Hello there, and welcome to Sleep Knowledge. I'm so glad you found your way here tonight. Maybe you've had a long day, one of those days where your mind hasn't stopped moving since morning. Maybe you're the kind of person who finds peace not in silence, but in the gentle exploration of deep thoughts and cosmic mysteries. Maybe counting sheep never quite worked for you, and instead, you find comfort in the vastness of space, in questions bigger than any single worry or concern. Whatever brought you here tonight, you're exactly where you need to be. You've got nothing to do but rest, nothing to solve, nothing to fix, nothing to prepare for. Just let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened its hold on you. Feel the weight of the day beginning to lift. Your shoulders can drop, your jaw can unclench, your thoughts can drift like clouds across an open sky. Because tonight, we aren't simply stargazing from a distance. We're drifting through our home galaxy, the Milky Way itself, a vast spiral of stars, dust, and dark matter, turning slowly in space for over 13 billion years. It's older than you can imagine, larger than your mind can hold, and yet somehow, impossibly, it's home. This galaxy, with all its beauty and mystery, is where you live. Where every human who has ever existed has lived. Where every story has unfolded beneath the same spiral arms. But beneath its beauty lie secrets. Rogue stars hurtling through darkness, invisible forces holding everything together, ancient stellar remains that defy what we thought we knew about time and creation. We'll travel gently tonight, from the galaxy's spiral arms to its secretive hidden core, from colossal collisions that happened billions of years ago to stars that are somehow older than the galaxy itself. You'll hear of black holes lurking at the center, of stellar nurseries glowing with newborn light, and of the strange, unfinished story of a galaxy that is still growing, still evolving, still becoming. Some of what you hear tonight may surprise you, or at the very least, it may spark some curiosity as you drift off to sleep, giving your mind something peaceful and vast to wander through in those quiet moments before dreams arrive. And just before we begin, if these calm, curious explorations help you unwind, if they give you a quiet way to end your day, consider liking and subscribing to Sleep Knowledge. It helps others find their way here, too, one sleepy soul at a time. Now, let your eyes close if they haven't already. Settle into your pillow, and let's begin our journey through the Milky Way. Our galaxy may feel like a stable home, a fixed point in an ever-changing universe, but that feeling is an illusion. The Milky Way is built from wreckage. It is stitched together from the ruins of other galaxies, smaller ones that wandered too close and were consumed. Over billions of years, our galaxy has absorbed dozens, perhaps hundreds of these smaller systems, drawing them in with its immense gravity, unraveling their structures, and scattering their stars into long tidal streams that wrap around the disk like ghostly ribbons. One such galaxy, the Sagittarius dwarf elliptical, is being pulled apart right now, at this very moment. As you lie here, its stars are being stripped away, one by one, stretched into a long stream that loops around our galaxy multiple times. It's a slow death, a cosmic unraveling that takes millions of years. The stars that once belonged to that galaxy are now becoming part of ours, absorbed into the Milky Way's structure, adding their light to the collective glow. And this is not the end of such encounters. Far off in the night sky, visible even to the naked eye under dark skies, the Andromeda galaxy is drifting slowly, steadily closer to us. It doesn't look like it's moving. From Earth, it appears as a faint, fuzzy patch of light, seemingly frozen in place, but appearances deceive. Andromeda is racing toward us at about 110 kilometers per second. That's over 400,000 kilometers per hour. and in about 4.5 billion years, give or take a few 100 million, the two great spirals will meet. When they do, it will be one of the most magnificent events in cosmic history. The collision will be gentle in the way only space can be gentle. Stars will almost never hit each other directly. The distances between them are too vast. But the galaxy's shapes will change forever, folding and stretching and warping under mutual gravitational pull. Spiral arms will be flung outward into space. New bursts of star formation will light up as gas clouds collide and compress. And eventually, after billions of years of this cosmic dance, the two galaxies will merge completely, forming a new structure altogether. Some astronomers have already given this future galaxy a name, Milky Way. Even galaxies, it turns out, are not eternal. They evolve, they collide, they die and are reborn. Some stars in the Milky Way are older than the Milky Way itself. Here's something that sounds impossible at first. Not every star in the Milky Way was born here. Some stars, ancient and wandering, appear to have formed even before the Milky Way had fully taken shape. These are the halo stars, and they drift in long, tilted orbits, high above and below the galactic plane, like elder spirits from a time before spirals, before order, before structure. How can a star be older than its own galaxy? The answer lies in how galaxies form. The Milky Way didn't appear all at once, fully formed. It grew over time, gathering mass, pulling in smaller clumps of stars and gas, slowly assembling itself from the chaos of the early universe. Some of the stars we see today were born in those smaller, primordial galaxies, tiny systems that formed shortly after the Big Bang and were later absorbed into what would become the Milky Way. Astronomers can identify these ancient stars by their chemical fingerprints. They contain almost no heavy elements, no iron, no carbon, no oxygen to speak of, just hydrogen and helium, the raw materials left over from the Big Bang. This tells us they were born in the universe's first few 100 million years, before generations of earlier stars had time to forge heavier elements in their cores and scatter them into space through supernova explosions. These stars move slowly and high above the galactic plane, tracing long, lonely orbits through the halo. They are metal-poor wanderers, relics of a younger, wilder cosmos. In their light, faint as it is, we see a universe that was still learning to become what it is. They are the oldest citizens of the galaxy, silent witnesses to its birth. Our solar system orbits the center at over 828,000 kilometers per hour. It's easy to forget, lying still in bed, that you are moving. Right now, at this very moment, you are spinning with the Earth as it rotates on its axis. You are also orbiting the Sun at about 107,000 kilometers per hour. But even that isn't the full picture. The Sun itself, along with the entire solar system, is sweeping through the Milky Way at an astonishing speed, more than 828,000 kilometers per hour. That's over 230 kilometers every single second. And yet, despite this incredible velocity, it takes about 225 million years to complete just one loop around the galaxy. This vast circuit is called a galactic year, and it puts our place in the cosmos into humbling perspective. In Earth time, we've only gone around the Milky Way about 20 times since the solar system formed 4.5 billion years ago. 20 times. That's all. Think about that for a moment. When the very first dinosaurs appeared on Earth, we were in a completely different part of the galaxy. The stars visible in their night sky, if they had been able to look up and contemplate them, were not the same stars we see today. The constellations we recognize, the patterns we've given names and stories to, they're temporary. They won't always remain. Over millions of years, stars drift apart. New neighbors arrive. old ones depart. Everything is in motion, quietly, slowly, endlessly. Even as you lie here, as your breathing slows and your muscles relax, the Earth continues its rotation. The moon circles in its orbit, the sun moves along its path, and the entire solar system sweeps forward through a galaxy that is itself in motion, spinning, evolving, colliding with the universe around it. You are part of a cosmic dance, so vast and so ancient that your entire life, every human life, every civilization, is just the briefest flicker within it. And yet here you are, conscious of it, aware of it, drifting through it even now as you drift toward sleep. The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. It's not a completed structure, frozen in time. Even now, at this very moment, it continues to grow. It gathers material from the space around it, gas from the intergalactic medium, stars from captured dwarf galaxies, streams of dark matter that feed its invisible halo. It grows not like a living thing, but like a gravitational structure, deepening over time, drawing in everything within its reach. Some of this growth happens quietly, almost invisibly. Thin clouds of gas drift inward from the vast spaces between galaxies, settling slowly into the disk, cooling and condensing over millions of years until they're dense enough to collapse and form new stars. This is gentle growth, a slow accumulation of raw material. Other times, growth comes with disruption. When a small satellite galaxy wanders too close, the Milky Way's gravity tears it apart. Its stars are scattered across the sky, smeared into long streams and arcs that trace the orbit of the doomed galaxy as it's slowly consumed. Some of these stellar streams have been mapped in exquisite detail by modern telescopes. They wrap around the Milky Way like ribbons, each one a memorial to a galaxy that no longer exists. The galaxy you live in today is not the same one the dinosaurs saw. Over the 165 million years that dinosaurs walked the Earth, the Milky Way consumed multiple smaller galaxies, added billions of new stars, and shifted its structure in subtle but real ways. In the galaxy your distant descendants may know, if humanity survives another billion years, it could be larger still, heavier still, stitched from the ruins of 1,000 smaller worlds. The Milky Way is not done. It is still becoming. We don't know how many arms the Milky Way has. It seems like something we should know. Something basic. How many arms spiral from the center of our own galaxy? But from our position deep inside the disk, embedded within the very structure we're trying to map, it's remarkably hard to see the whole picture. It's like trying to understand the layout of a city while standing in the middle of a crowded street, unable to rise above it, unable to step back and see it from a distance. Dust clouds obscure distant regions of the galaxy. Stars blur into one another when we look along the plane. For decades, astronomers believed there were 4 major spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. More recent observations, using infrared telescopes that can peer through dust, suggested maybe there are only 2 major arms, with several smaller segments branching off. But even that isn't certain. Some arms appear to fade into fragments as you follow them. Others wrap around unexpectedly or split into multiple lanes. The Milky Way may not be a neat pinwheel at all, the kind you see in textbook illustrations. It might be something messier, more complex. A living layered swirl of stars shaped by forces we still don't fully understand. Dark matter, gravitational resonances, ancient collisions, and the slow churning of galactic rotation. We're still mapping our home, still learning its shape, and there's something beautifully humbling about that. Chapter 2: Rogue Stars and Cosmic Exiles. Rogue stars are flung from the core. Most stars drift calmly through the galaxy, following gentle orbits that last hundreds of millions of years. They move in predictable paths, held by gravity, part of the great wheel of the Milky Way. But a rare few stars are different. They are flung outward at astonishing speeds, fast enough to escape the galaxy entirely. These are hypervelocity stars, and they are among the most dramatic events in the Milky Way's ongoing story. Some of these rogue stars are the remnants of binary systems that wander too close to the supermassive black hole at the galaxy's center. In a binary system, two stars orbit each other, bound together by mutual gravity. But when such a pair drifts too near Sagittarius A asterisk, the black hole at the heart of the Milky Way, something violent can happen. The black hole's immense gravity tears the binary apart. One star is captured, falling inward, spiraling down past the event horizon and vanishing forever. The other star is flung outward with tremendous force, slingshot into the dark at over 1,000,000 kilometers per hour. These ejected stars don't slow down. There's nothing to stop them. They hurtle through the disk, through the halo, and eventually out into intergalactic space. They travel alone, far from the galactic plane, like glowing comets with no return ticket. Some will wander the void between galaxies for billions of years, carrying the Milky Way's light into the cosmic dark. They remind us that even in a galaxy, bound by gravity, bound by structure, there are moments of violent release, quiet expulsions, stars sent flying into the intergalactic night, never to return home. The Milky Way and Andromeda are on a collision course. We've mentioned this already, but it's worth dwelling on. High above the horizon on autumn nights, if you know where to look, the Andromeda galaxy appears as a faint blur to the naked eye. It's the most distant object you can see without a telescope, lying over 2.5 million light-years away. A spiral much like our own. A galaxy with its own hundreds of billions of stars, its own supermassive black hole, its own history of collisions and growth, and it is moving steadily toward us. The collision won't happen in your lifetime, not in your children's lifetimes, nor in 1,000 generations of human descendants. But in about 4.5 billion years, the Milky Way and Andromeda will collide. It won't be violent in the way you might imagine. No stars will crash into each other. The distances between stars are simply too vast. If you could somehow live through the collision, standing on Earth and watching the sky, you might see Andromeda grow larger and brighter over millions of years, eventually dominating the night sky, a blazing spiral stretching across the heavens. As the galaxies interpenetrate, their gravity will warp both structures into long, stretching arcs. Tidal tails will curl outward like ribbons. Star formation will surge as gas clouds collide and compress. The supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging into a single, even more massive black hole. And after billions of years of this slow, elegant dance, the two galaxies will merge completely into a single larger system. It will likely be an elliptical galaxy, no longer a spiral, a new structure, a new beginning. The future of our cosmic home is written across the stars, and it involves a collision with our nearest galactic neighbor. Some stars orbit backward. Most stars in the Milky Way orbit the galactic center in the same general direction, flowing together like a vast river of light. This is the result of the galaxy's rotation, a product of how it formed from a spinning cloud of gas billions of years ago. But not all stars follow the rules. Some stars, especially in the outer halo, move in retrograde. They orbit in the opposite direction, swimming against the current. These backward orbiting stars likely arrived from elsewhere. They were born in dwarf galaxies that were later absorbed by the Milky Way, and they retained their original motion even as their home galaxy was torn apart. Their reversed motion is a quiet signature of their foreign origin, a fingerprint of ancient mergers. It's as if the galaxy carries old memories in its motion, stories of cosmic encounters preserved not in light or matter, but in the slow, patient turning of stars against the stream. These retrograde stars are immigrants from destroyed worlds, still following paths they were set on billions of years ago. The Milky Way may have eaten dozens of dwarf galaxies. Over billions of years, the Milky Way has not grown alone. It has consumed. Small galaxies, faint luminous companions orbiting in the halo, have drifted too close, been caught in our gravity, and slowly dismantled. Their stars are now part of our halo, our disk, or the stellar streams that wrap around the galaxy like memory. Astronomers have identified several of these ancient mergers by analyzing stellar motion and chemical composition. One especially significant event, the Gaia-Enceladus merger, occurred about 10 billion years ago. A dwarf galaxy with perhaps 10 billion stars collided with the young Milky Way, and its stars were scattered throughout what is now the inner halo. This merger may have reshaped the early structure of the galaxy, puffing up the disk and adding a significant population of stars. The Milky Way is not a pristine spiral born in isolation. It is a composite, a mosaic, built from quiet collisions and stitched together from the remains of many smaller worlds. Our galaxy is an archive, a living museum of cosmic violence preserved in the motion and chemistry of stars. Chapter 3, Reading the Stars. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth that tells the story of where and when it formed. By studying these signatures, which show up as dark lines in a star's spectrum, astronomers can trace a star's history with remarkable precision. Some stars are rich in heavy elements like iron, calcium, and nickel. These are called metal-rich stars, and they suggest formation in dense, chemically enriched regions where previous generations of stars had already lived and died, scattering their forged elements into space. These stars are typically younger, born from gas clouds that had been seeded with the products of supernova. Other stars are nearly pure hydrogen and helium, with barely a trace of anything heavier. These metal-poor stars were born when the universe was still young, before the cosmic furnaces had had time to create many of the heavier elements. They are ancient, some more than 12 billion years old, and they formed in environments vastly different from the star-forming regions we see today. These differences allow scientists to group stars into families, to uncover ancient mergers, and to reconstruct the hidden story of the Milky Way's formation. In this way, chemistry becomes a kind of time machine. By reading the light from distant stars, we can peer back billions of years and see the galaxy as it once was. It's like reading ancient poetry written in light. The sky is full of stellar streams from shredded galaxies. Across the sky, barely visible even with powerful telescopes, thin ribbons of stars stretch in long arcs and graceful curves. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart by tidal forces. As these doomed galaxies orbit, their stars are smeared across space, forming delicate trails that trace their former paths. Some streams wrap around the galaxy like ghostly halos. Others dive in toward the core, threading through the disk. Each stream is a memorial to a galaxy that no longer exists. The Sagittarius stream, for example, loops around the Milky Way multiple times. The scattered remains of the Sagittarius dwarf elliptical galaxy, which is still being torn apart today. These streams are evidence of past collisions, quiet mergers that built the Milky Way over billions of years. The galaxy, like a tree, carries the rings of its past in every thread of light, every faint arc of stars. If you could see the full sky in exquisite detail, mapping every faint star, you would see dozens of these streams crisscrossing the heavens, each one telling a story of consumption and transformation. The Milky Way is not just a galaxy, it's a graveyard and a nursery all at once. The Milky Way's warped, Our galaxy doesn't lie flat like a perfect spiral in a textbook illustration. Its disk bends upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warp was invisible to us until radio telescopes mapped the distribution of hydrogen gas, which stretches far beyond the visible starlight into the outer reaches of the galaxy. Astronomers believe the distortion may be caused by the gravitational pull of satellite galaxies, like the Magellanic Clouds, tugging gently on the Milky Way's edges. Or it might be the influence of clumps of dark matter in the halo, bending the disk from below. Some models suggest that the warp is dynamic, rotating slowly like a wave moving through the structure. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still. Over time, they bend, they flex, they change form in response to invisible forces. From a distance, if you could step outside the galaxy and look back at it, the Milky Way might look like it's dancing slowly through space. And in a way, it is. Chapter 4, Observing the Invisible. You can only see about 0.00003% of the Milky Way with the naked eye. Under a clear, dark sky, far from cities and streetlights, far from the orange glow of light pollution, you might see a few thousand stars scattered across the heavens. To the human eye, that seems like an ocean of light, a vast multitude, but it's barely a droplet. The Milky Way contains over 100 billion stars. Some estimates put it closer to 400 billion. Most of those stars are hidden from view. Some lie behind thick curtains of interstellar dust. Others are simply too faint or too far away for our vision to reach. And many exist in wavelengths of light our eyes cannot perceive. Infrared, ultraviolet, X-rays, radio waves. The pale streak of the Milky Way that crosses the sky on moonless nights, that soft glowing band that inspired myths and legends in every human culture, is just the innermost whisper of the whole. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us. It's too vast to grasp from within, too immense to hold in a single glance. We see only the tiniest fraction of what's really there. And even that tiny fraction is enough to fill us with wonder. Stars orbit the galaxy at different speeds. Unlike planets in a solar system, which follow Kepler's laws and move in predictable, orderly paths around their star, stars in the Milky Way move with more freedom and complexity. Some race ahead in the inner regions, completing orbits in just a few million years. Others drift slowly along the outskirts, taking hundreds of millions of years to complete a single loop. This difference in orbital speed is why spiral arms form in the first place. They're not solid structures, not fixed lanes of stars rotating together. Instead, they're patterns, density waves, regions where stars and gas temporarily bunch up, like slow-moving traffic jams on a cosmic highway. As stars move through these density waves, they slow down slightly, bunch together, and then speed up again as they exit the other side. It's this bunching that makes the arms visible. Gas clouds passing through these regions are compressed, and the compression triggers new bursts of star formation. Young, bright, blue stars light up the arms in curls of radiant light. Our own sun is part of this swirl. It's moving in and out of these patterns across time, spending millions of years inside a spiral arm, then millions more drifting through the spaces between. The galaxy is not a clock, it's not rigid or mechanical. It's a current, a flow, and we are drifting in it. The galaxy holds together because of something we cannot see. By all logic, the Milky Way should not exist. Based on what we can measure, the mass of stars, dust, and gas, the outer edges of the galaxy are spinning far too fast. They should be flung into space, scattered like leaves in a storm. The visible matter simply isn't heavy enough to hold everything together, and yet the galaxy remains stable, rotating, intact. The answer is dark matter. This mysterious, invisible substance does not shine. It does not reflect or emit any light. It does not interact with ordinary matter except through gravity. But there is so much of it, filling a vast halo around the galaxy, that it outweighs all the visible matter many times over. We don't know what dark matter is. Decades of experiments have failed to detect its particles directly. It could be made of something we've never encountered before, something fundamentally different from the atoms and molecules we're familiar with. But we know it's there because of what it does. Without dark matter, the Milky Way would fly apart. It is the invisible scaffolding that holds everything in place, the hidden foundation of the galaxy's existence. Chapter 5, The Heart of Darkness. There's a supermassive black hole at the core. At the very center of the Milky Way, hidden behind vast curtains of dust and gas, lies an enormous black hole, a singular point of gravity so intense that nothing, not even light, can escape once it crosses a certain boundary. This object is called Sagittarius A asterisk, pronounced Sagittarius A star, and it is more than 4 million times the mass of our Sun. Yet despite this incredible mass, it occupies a space smaller than the orbit of Mercury. All of that matter, all of that gravitational pull, compressed into a region just a few million kilometers across. It's almost impossible to imagine a point in space where the rules break down, where time itself warps and stretches, where the universe reveals its most extreme physics. We cannot see Sagittarius A times directly. Black holes, by their very nature, are invisible, but we've watched nearby stars whip around it at tremendous speeds, tracing invisible loops through the void. Some of these stars complete full orbits in just 16 years, racing at speeds approaching a significant fraction of the speed of light. By tracking their motion, astronomers have mapped the black hole's position and calculated its mass with extraordinary precision. Sometimes, gas and dust fall inward toward the event horizon, spiraling down in a glowing accretion disk. As this material accelerates and heats up, it flares with X-rays and other high-energy radiation before disappearing forever beyond the point of no return. These flares are brief but brilliant, lighting up the galactic center for hours or days before fading back into darkness. For now, Sagittarius A time sleeps. It's relatively quiet compared to black holes in other galaxies, consuming only small amounts of material. But long ago, it may have burned like a quasar, a blazing beacon of light fueled by torrents of infalling matter, lighting up the galaxy from within with a brilliance that outshone all the stars combined. It is the silent conductor of the Milky Way's heart, pulling stars into slow, relentless orbits, waiting patiently in the dark. The Milky Way has a peanut-shaped bulge. When astronomers mapped the center of the galaxy using infrared light, which can penetrate the dust that blocks visible wavelengths, they discovered something unexpected. The central bulge, the dense concentration of stars at the galaxy's heart, is not a smooth, round ball. Instead, it has a three-dimensional peanut shape, or what some describe as a box shape when viewed from certain angles. Seen from the side, it swells in the middle and narrows at the ends, like a twisting hourglass made of billions of stars. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly through the core. Over time, gravitational forces cause the bar to buckle vertically, puffing upward and downward, creating this distinctive bulging shape. These inner structures are sculpted by gravity, by billions of years of motion, by the accumulated rhythm of countless stellar orbits all influencing each other. The mathematics of it is complex, involving resonances and instabilities that play out over cosmic timescales. We live in a spiral galaxy, yes, but its heart is full of complexity and asymmetry, not flat or clean or simple, but intricate and alive with structure. The more closely we look at the galactic center, the more we realize how dynamic and layered it truly is. Stellar nurseries shape the spiral arms. The Milky Way's spiral arms are not simply made of stars, frozen in place like paint on a canvas. They're woven from the birthplaces of stars, from the raw materials of creation itself. Giant clouds of hydrogen, molecular gas, and dust drift through the galaxy, some spanning hundreds of light years across. These are the stellar nurseries, and they are where new suns are born. When these clouds pass through the density waves that form the spiral arms, something remarkable happens. The gas is compressed, squeezed by the increased gravitational pressure. This compression causes regions within the clouds to collapse under their own weight, fragmenting into smaller clumps. Each clump grows denser and hotter as it falls inward, spinning faster until finally the core ignites with nuclear fusion. A new star is born. These regions are chaotic, glowing, and full of motion. Ultraviolet light from the newly born stars floods outward, illuminating the surrounding clouds and painting them with radiant blues, purples, and silvers. The brightest young stars, massive and short-lived, carve out cavities in the gas with their powerful stellar winds, creating bubbles and pillars of sculpted nebulosity. These bursts of star formation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star you see in the night sky, including our own sun, was born from one of these cloudy cradles long ago. The spiral arms are not just structures, they are the places where the galaxy remakes itself, generation after generation. The Milky Way is surrounded by a vast halo. Beyond the flat spiral disk, beyond the bright concentration of stars we think of when we picture the galaxy, lies something far more diffuse and mysterious, a spherical halo that surrounds the entire Milky Way like an enormous, nearly invisible bubble. This halo contains ancient stars scattered thinly across vast distances. It contains globular clusters, dense spheres of hundreds of thousands of stars, orbiting in long, slow arcs that rarely touch the disk. And it contains enormous amounts of dark matter, perhaps the majority of the galaxy's total mass, forming an invisible scaffolding that extends far beyond the visible edges. The stars in the halo are spread thin, separated by distances that dwarf the spaces between stars in the disk. They orbit on highly elliptical paths, some climbing tens of thousands of light years above the galactic plane before falling back down again, spending most of their time far from the crowded center. The halo also preserves the remnants of ancient galactic mergers, stellar streams and shells of stars torn from smaller galaxies and left behind like cosmic fossils, wrap around the Milky Way in complex patterns. Each stream tells a story of a galaxy that came too close, that was captured and dismantled. Its star is now part of our halo's sparse population. It is the galaxy's outer memory, quiet and dim, but still in motion, still shaping what the Milky Way becomes. The halo is where the past lingers, where ancient collisions leave their traces, where the oldest stars drift like echoes from the universe's early days. It contains over 150 globular clusters. Globular clusters are among the oldest and most beautiful objects in the galaxy. They are compact spheres made of hundreds of thousands, sometimes millions, of tightly bound stars, packed together so densely that if you lived on a planet within one, the night sky would be filled with brilliant suns, bright enough to cast shadows even at night. These clusters orbit the galactic center in the halo, sweeping through space like moths circling a distant flame. They follow long elliptical paths that take them far above and below the disk, through the sparse outer reaches of the galaxy. Some pass through the disk itself, briefly, before climbing back out into the halo. These clusters are incredibly stable. Some are more than 12 billion years old. nearly as old as the universe itself. Many contain stars that predate the Milky Way's disk, stars that formed when the galaxy was still assembling from smaller fragments. Their stars are metal poor, containing only trace amounts of elements heavier than helium, meaning they formed before the universe had time to create many of the building blocks of planets and life. They serve as time capsules, holding clues to how the galaxy formed, what it consumed, and what conditions were like in the early cosmos. Their perfect spherical shapes, their internal dynamics, the way their stars interact, all of this tells us about gravity, stellar evolution, and the ancient past. These quiet, golden spheres drift patiently above and below the galactic plane, glowing softly in the dark, unchanged for billions of years. Chapter 6: Growth and Renewal. The galaxy is still growing. We mentioned this earlier, but it bears repeating because it's so counterintuitive. Although the Milky Way is ancient, unimaginably old, it isn't finished. It's not a completed structure, frozen in time like a museum piece. Even now, at this very moment as you rest, it continues to gather material and grow. Gas flows in from the intergalactic medium, thin streams of hydrogen and helium drawn inward by the galaxy's gravity. These filaments, part of the vast cosmic web that connects all galaxies, feed the Milky Way with fresh fuel for star formation. Some of this gas arrives cold, slipping quietly into the disk. Other streams are shock-heated as they fall, glowing in ultraviolet and X-ray wavelengths. Stars are captured from dwarf galaxies that wander too close, the Sagittarius dwarf, the Canis Major dwarf, and others are slowly being absorbed, their stars added to the Milky Way's total count. Even now, streams of stars from these disrupted galaxies are raining down onto the disk and halo, becoming part of our galaxy's structure. Streams of dark matter flow inward as well, invisible but gravitationally significant, adding to the massive halo that holds everything together. The galaxy grows not like a living thing, not with intention or purpose, but like a gravitational structure deepening over time, accumulating mass, becoming denser and more complex. Some of this growth happens quietly through slow infilling of diffuse clouds. Other times it comes with disruption, with violent encounters that shake the disk and trigger bursts of new star formation. The galaxy you live in today is not the same one the dinosaurs saw 100 million years ago. It was lighter then, less massive, with fewer stars. And the one your distant descendants may know, if they exist a billion years from now, could be larger still, stitched from the ruins of dozens of smaller worlds that have yet to fall. Rogue stars are flung from the core. Most stars drift calmly through the galaxy, following gentle, predictable orbits shaped by the combined gravity of billions of other stars and the dark matter halo. But a rare few are different. A rare few are flung outward at astonishing, almost incomprehensible speeds, fast enough to escape the Milky Way entirely. These are hypervelocity stars, and they represent some of the most extreme dynamics in the galaxy. Some are the remnants of binary systems disrupted by the supermassive black hole at the center. Imagine two stars, bound together, orbiting each other for millions or billions of years. They drift too close to Sagittarius A*, pulled by its immense gravity. The tidal forces stretch and distort the binary system. One star falls inward, captured by the black hole, spiraling down past the event horizon and vanishing forever into the darkness. The other star is slingshot outward with tremendous force, flung into space at over 1,000,000 kilometers per hour, sometimes exceeding 1,700 kilometers per second. Other hypervelocity stars may be ejected by supernova explosions in binary systems or by gravitational interactions in dense star clusters where three or more stars pass close to each other and one is violently ejected. These rogue stars travel alone, far from the galactic plane, far from the spiral arms, like glowing comets with no return. They hurtle through the halo and eventually out into intergalactic space, carrying the Milky Way's light into the cosmic void. Some will wander the darkness between galaxies for billions of years, solitary travelers in an almost unimaginably vast emptiness. They remind us that even in a galaxy bound by gravity, structured and orderly, there are moments of violent release, quiet expulsions, stars sent flying into the intergalactic night, never to return home. Star formation is slowing down. Long ago, billions of years in the past, the Milky Way was more active, more vibrant. It was bursting with fresh stars, born from dense, collapsing clouds throughout the disk. The rate of star formation was much higher then, perhaps 10 times what it is today. The galaxy was younger, more energetic, filled with massive blue stars that burned bright and died young. But in recent epochs, the pace is slowed. There is still gas available for star formation, still vast molecular clouds drifting through the spiral arms, but much of it is spread thin, heated by radiation from existing stars, or locked in forms that resist collapse. The dense clouds that collapse most readily have already done so. What remains is more diffuse, harder to compress, less efficient at forming stars. The galaxy is not done making stars, far from it. New suns are still being born every year, perhaps a few solar masses worth, but it is settling, entering a quieter chapter. Astronomers estimate that star formation peaked billions of years ago and has been declining ever since, following a gentle downward curve. This does not mean the end is near. The Milky Way likely has fuel for billions more years of star formation, but we live in a mature phase, a middle-aged galaxy that is no longer in its explosive youth, a spiral glowing gently in its prime, still forming stars, but no longer in a hurry. The frantic creativity of youth has given way to a slower, steadier rhythm. Some stars formed before the Milky Way had a disk. The disk, that broad, flat spiral we think of as the defining feature of the Milky Way, formed gradually over time. It wasn't there at the beginning. In the earliest days, the proto-galaxy was a loose, chaotic cloud of gas, dark matter, and the first generation of stars, all swirling together without much structure. But some of the stars in our galaxy are older than the disk itself. These ancient suns reside mostly in the halo, or in what's called the thick disk, a puffier, older layer that lies above and below the thin disk where we live. They formed when the galaxy was still assembling, still collapsing inward, before rotation and angular momentum had flattened things into a neat plane. By studying their composition and motion, astronomers can peer back into this era before structure, before spirals, before the Milky Way looked anything like it does today. These stars move on different orbits, more random, more tilted, because they formed in a different kind of environment. They are the elders of the galaxy, silent witnesses to its birth and the long, slow shaping of what we now call home. In their light, we see not the Milky Way as it is, but as it was. A glimpse of our galaxy in its infancy. Chapter 7, The Rhythm of Orbits. A galactic year is about 225 to 250 million Earth years. As the Sun orbits the center of the Milky Way, sweeping along its curved path through space, it completes one full revolution every few 100 million years. This fast cycle of motion is called a galactic year, and it dwarfs all our human timescales so completely that it's almost impossible to grasp. In the time it takes for the Sun to circle the galaxy once, continents drift across the surface of the Earth, colliding and breaking apart. Mountain ranges rise and erode away. Entire epochs unfold in the fossil record. Species rise, flourish, and go extinct, replaced by new forms of life. When the Sun was last in this part of its galactic orbit, roughly where it is now, it was about 225 million years ago. The supercontinent Pangaea was just beginning to break apart. Dinosaurs had not yet emerged. The dominant land animals were early reptiles and synapsids, distant relatives of mammals. The Earth was a very different place. And before that, another 225 million years earlier, the Sun was in the same general region of the galaxy, but life on Earth was even more alien. Primitive amphibians were just beginning to colonize the land. Plants were simple. The oceans teemed with strange arthropods and early fish. A galactic year is the slow heartbeat of cosmic time, a rhythm so vast that entire geological eras are just brief moments within it. The Sun has completed fewer than 25 galactic orbits. In all of its 4.6 billion years of existence, the Sun has only circled the Milky Way around 20 to 21 times. That's fewer than you might expect considering its incredible speed of nearly 830,000 kilometers per hour through space. But the galaxy is so vast, the path so long, that each orbit takes hundreds of millions of years. We often think of the stars as ancient and unmoving, as fixed points that have been there forever. But our solar system is still relatively young on a galactic scale. It's a newcomer in a city of older, more traveled suns. Many of the stars in the halo have completed far more orbits, having been around since the galaxy's early days. We are part of the galaxy's motion, participants in its great turning, but we're still early in its long, winding story. If the Milky Way lives for another 100 billion years, as some models suggest it might, slowly consuming its remaining gas and forming ever fewer stars until it becomes a quiet collection of red dwarfs and dead remnants, then the Sun's brief life represents less than 5% of that total span. We are here in the galaxy's prime, in its most active and luminous era. And even within that prime, we've only been around for 20 laps, 20 circuits of this enormous wheel. The Milky Way's rotation defies Newton's predictions. According to Newtonian physics, according to the laws of gravity that govern planets orbiting the Sun, stars farther from the galactic center should orbit more slowly than those near the center. Just as Neptune moves more leisurely around the Sun than Mercury, outer stars should lag behind inner ones. But in the Milky Way, something strange happens. Stars in the outer regions orbit almost as quickly as those near the center. The rotation curve, as astronomers call it, stays flat rather than dropping off as expected. This defies classical expectations. The visible matter in the galaxy simply isn't heavy enough or distributed in the right way to explain this behavior. The reason, as we've touched on before, is dark matter, an invisible, unknown form of mass that surrounds the galaxy in a vast halo, extending far beyond the visible disk. This dark matter halo is so massive, containing perhaps 10 times as much mass as all the visible stars and gas combined, that it changes the gravitational landscape entirely. With dark matter included, the math works. The flat rotation curve makes sense. The galaxy holds together as it should. But without dark matter, the Milky Way would tear itself apart, flinging its outer stars into intergalactic space within a few 100 million years. The galaxy turns like a solid wheel, rotating almost as one piece, not because we understand it fully, but because something unseen is holding it in place, binding it together with invisible gravity. The galaxy has enormous molecular clouds, scattered throughout the Milky Way, hidden in the spaces between stars, are vast, dark clouds of cold gas. These molecular clouds, composed mostly of hydrogen molecules with traces of carbon monoxide, dust, and other compounds, can span hundreds of light years across. They're some of the largest structures in the galaxy. Within their cold, dense interiors, shielded from starlight and radiation, temperatures drop to just a few degrees above absolute zero. This extreme cold allows molecules to form and survive, building up complex chemistry. These clouds are the raw material of stars, the reservoirs from which new solar systems are born. Some of these clouds are so large and so cold that they absorb visible light entirely, appearing as black patches against the starry sky, dark silhouettes that block our view of stars beyond. The Coalsack Nebula, visible from the southern hemisphere, is one such cloud, a dark splotch in the otherwise bright band of the Milky Way. They are the galaxy's wombs, quiet, hidden places where the future begins in silence, tucked within curtains of shadow and gas. Without these clouds, there would be no new stars, no new planets, no new chances for life to emerge. The galaxy would slowly grow dim as existing stars aged and died, with nothing to replace them. Supernovae stir the galaxy like storms. When massive stars reach the end of their lives, having fused elements all the way up to iron in their cores, they can no longer generate energy through fusion. The core collapses in a fraction of a second, and the outer layers rebound in a cataclysmic explosion. A supernova, an event so powerful it can outshine entire galaxies for a brief moment, releasing as much energy in a few weeks as the sun will emit over its entire 10 billion year lifetime. These explosions don't just end lives. They create. They transform. They fundamentally reshape their environment. Shock waves from supernovae ripple through the interstellar medium at thousands of kilometers per second, compressing nearby clouds and triggering new waves of star formation. The compressed gas collapses faster than it would naturally, giving birth to new stars that might not have formed otherwise. Supernovae also enrich the surrounding space with heavy elements: carbon, oxygen, silicon, iron, gold. All the elements heavier than helium are forged in the cores of stars or in the explosions themselves. These elements are blasted outward into space, mixing with the interstellar medium, seeding future generations of stars and planets with the building blocks of complexity. In this way, supernovae act like storms within the galactic ecosystem. They stir the gas, they fertilize the clouds with heavy elements, they reshape everything around them. They are the galaxy's moments of chaos, violent and radiant, but also necessary. Without supernovae, the galaxy would be a very different place. Simpler, quieter, less capable of forming rocky planets or complex chemistry or life as we know it. Chapter 8. Hidden Structures. Dust hides vast regions of star formation. The Milky Way is full of light we cannot see. Interstellar dust, made of microscopic grains of carbon, silicon, iron, and ice, weaves through the galaxy in clouds and tendrils. In visible light, this dust is opaque, blocking and scattering starlight, obscuring vast regions of space and making them appear dark and empty. But behind this veil, star formation continues. Hidden from visible wavelengths, stellar nurseries glow with newborn suns, gas clouds collapse and fragment, and entire clusters of massive stars illuminate their surroundings with intense radiation. Infrared telescopes can peer through the dust, revealing these hidden regions in exquisite detail. What looks like darkness in visible light transforms into blazing complexity in infrared. Glittering nurseries filled with protostars, glowing pillars of gas sculpted by stellar winds, and dense cores on the verge of collapse. The dust, though it hides, is part of the process. It absorbs ultraviolet and visible light from nearby stars, converting it to heat, and this gentle warming can actually help gas cool and collapse more efficiently in certain regions. The dust also provides surfaces where molecules can form, building up the complex chemistry needed for planets and potentially life. What seems like emptiness, what appears as black voids in photographs, is often the beginning of something bright. The dust doesn't mark the absence of creation, it marks its hidden presence. There are starless gas clouds drifting through the galaxy. Not every cloud of gas becomes a star. Across the Milky Way, astronomers have found massive cold clouds that seem destined for collapse, that contain enough material to form thousands of stars, yet remain dark and dormant. Some are too diffuse, their gravity too weak to overcome internal pressure and turbulence. Others may be stabilized by magnetic fields threading through them, providing support against collapse. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen but untouched by fusion. They may one day ignite, triggered by a passing shockwave from a supernova, or by a collision with another cloud, or by the gravitational squeeze of passing through a spiral arm, or they may drift until torn apart by external forces, their gas recycled into other regions, absorbed into other structures. In these clouds, the galaxy holds its breath, waiting, perhaps, for the right nudge to spark something new, or perhaps content to let them wander, reservoirs of potential that may never be realized, at least not yet. The galaxy is patient. It has time. The Milky Way recycles matter across generations. Stars are not permanent. They live, they burn, and they die. And in dying, they return their material to the galaxy, completing a grand cycle that has been ongoing for billions of years. Supernovae spread heavy elements across vast regions. Red giants shed their outer layers in gentle stellar winds, creating planetary nebulae that glow for thousands of years before fading. Even white dwarfs, the cooling cores of dead stars, slowly release their heat back into space over trillions of years. This enriched material joins the interstellar medium, mixing with existing gas and dust, where it cools, condenses, and eventually forms new stars and planetary systems. Each generation of stars adds more heavy elements to the mix. The first stars were almost pure hydrogen and helium, but by now, after billions of years of stellar death and rebirth, the interstellar medium is seeded with carbon, oxygen, nitrogen, iron, and all the other elements needed for planets and life. Every atom in your body has passed through this cycle, most likely multiple times. The calcium in your bones was forged in the core of a massive star that exploded billions of years ago. The iron in your blood was created in a supernova. The oxygen you breathe was made inside a giant star and released into space when it died. Even the hydrogen in the water that makes up most of your body dates back to the Big Bang itself, but it's been incorporated into stars and planets multiple times since then. The Milky Way is not a static stage where events unfold. It's a great engine of renewal. It breathes in time with its stars, making and unmaking and beginning again. The galaxy is constantly dying and being reborn, each cycle adding more complexity, more possibility. You are made of star stuff, as Carl Sagan famously said. And that's not poetry, it's literal truth. Metal-poor stars hold clues to the early universe. In astronomy, the term metal doesn't mean what it does in everyday language. To astronomers, metals are any elements heavier than helium. So carbon is a metal, oxygen is a metal, iron, silicon, nitrogen, all metals in astronomical terminology. This might seem strange, but it reflects the history of the universe. In the beginning, right after the Big Bang, the universe contained only hydrogen, helium, and tiny traces of lithium. That's it. Everything else, every other element on the periodic table, had to be forged later in the cores of stars or in explosive events. The earliest stars in the universe, the first generation born a few 100 million years after the Big Bang, had almost no metals at all. They were pristine, made of primordial gas. Today, astronomers seek out metal-poor stars in the halo of the Milky Way, ancient suns with only trace amounts of heavy elements. These stars preserve the chemical conditions of a time long gone. By analyzing their composition, their spectra, the patterns of absorption lines in their light, we can peer into the primordial past. We can see what the universe was like before galaxies had matured, before multiple generations of stars had enriched the cosmos with heavy elements, before the galaxy itself had taken full shape. These stars are fossils, but fossils made of light. They're ancient messages from the early universe, still shining, still telling their stories to anyone willing to listen. Some stars wander far from where they were born. A star's birthplace doesn't always define its destiny. Over time, over millions or billions of years, many stars drift away from their natal clouds, pushed and pulled by gravitational interactions, by the slow churn of the galaxy's rotation, by orbital resonances with spiral arms, or by encounters with other stars and gas clouds. Some stars are ejected at high speeds from their birth clusters, flung across the disk or into the halo. These might be stars that were part of binary systems disrupted by close encounters, or stars accelerated by the collective gravity of a dense cluster in complex three-body interactions. Others migrate gradually, shifting their orbits inward or outward over millions of years as they spiral through the galaxy and interact with the gravitational field of the disk and spiral arms. The Sun's orbit, for instance, isn't perfectly stable over hundreds of millions of years. It oscillates, moving slightly inward and outward, rising and falling through the galactic plane. Even our Sun is not where it began. Tracing its path backward, based on its current motion and velocity, suggests it may have formed in a different part of the galaxy entirely, perhaps closer to the center than we are now. Its birth cluster has long since dissolved, its siblings scattered. Tracing the paths of stars, mapping their motion through the galaxy, reveals a Milky Way that is anything but static. A galaxy alive with movement, exchange, and quiet dislocation. Home, for a star, may only be temporary. The galaxy's habitable zone may span tens of thousands of light years. Just as Earth orbits in a Goldilocks zone around the Sun, not too hot and not too cold for liquid water to exist on its surface, the Milky Way may have its own galactic habitable zone, a broad region where conditions are most favorable for life to emerge and survive over billions of years. This zone is thought to lie somewhere between the dangerous inner core, full of radiation from the supermassive black hole and frequent supernovae in densely packed stellar neighborhoods, and the sparse metal-poor outer edges, where planets may be harder to form due to lack of heavy elements. Somewhere in between lies a wide band, perhaps spanning tens of thousands of light years, where conditions are more stable, star density is moderate, so catastrophic encounters are rare. Supernovae happen, but not so frequently that they sterilize planets every few million years. Heavy elements are abundant enough to form rocky worlds with complex chemistry. Earth lies within this zone, about 26,000 light-years from the galactic center. One quiet orbit in a vast swirl where life might not be alone in finding a foothold. If this idea is correct, then there could be billions of habitable worlds in the Milky Way, spread throughout this broad ring, each one orbiting its own star under the same spiral arms. We don't know yet if we're unique, but the galaxy has plenty of room for company. Chapter 9. The Architecture of Spirals. The spiral arms are not fixed structures. The Milky Way's spiral arms might seem like permanent features, grand sweeping lines carved into the galaxy's disk like grooves in a cosmic record. But they are not made of fixed stars traveling together in formation. Instead, they are patterns, waves of density that ripple slowly through the disk, compressing gas and triggering bursts of star formation as they pass. Think of it like a traffic jam on a highway. Individual cars move through the jam at their own speeds, entering from behind, slowing down in the middle, and accelerating out the front. But the jam itself, the pattern of congestion, moves at a different speed than any individual car. The jam persists, even though the cars within it are constantly changing. Spiral arms work the same way. Stars drift into these density waves, slow down slightly as they pass through the compressed region, brighten the arm with their presence, and then drift out again on the other side. Meanwhile, the density wave itself rotates at a different, slower speed, maintained by the gravitational structure of the galaxy. Gas clouds passing through these density waves are compressed, and this compression triggers the collapse that forms new stars. The youngest, brightest, most massive stars are found in the spiral arms because that's where they're currently being born. These massive blue stars live only a few million years, so they don't have time to drift far from their birthplace before they die. They mark the spiral arms like brilliant signposts. From afar, looking at the galaxy from outside, it looks like form and order. Neat spiral curves sweeping around the center. But from within, from our perspective, it's a pattern of shifting motion held together by gravity and time, never still, always flowing. The spiral arms are not roads, they're waves passing through an ocean of stars. The Milky Way hums with cosmic radiation, beyond visible light, beyond what our eyes can perceive. The galaxy glows with more mysterious and energetic forms of radiation. Cosmic rays, high-energy particles born in supernova explosions and accelerated to nearly the speed of light by magnetic fields, stream through space in all directions. They pass through your body constantly, every second of every day. Billions of them, most without any interaction at all. X-rays and gamma rays shimmer from dying stars, from black holes consuming matter, from neutron stars in binary systems where gas is heated to millions of degrees before being swallowed. Radio waves drift from cold gas clouds, from pulsars spinning hundreds of times per second, from the cold whisper of hydrogen distributed throughout the disk. These invisible wavelengths reveal what visible light cannot, the violence and energy hidden behind the beauty, the magnetism threading through the interstellar medium, the ancient fires still flickering within the galaxy's structure, often in places that appear dark and quiet in visible light. When you look into the night sky with your eyes, you're only seeing a narrow band of the Milky Way's true spectrum, a thin slice of reality. But the galaxy exists in all wavelengths simultaneously, radiating across the entire electromagnetic spectrum. If you could see in X-rays, the galactic center would blaze like a furnace. If you could see in radio waves, vast arcs and loops would span the sky, shaped by magnetic fields and ancient explosions. Beneath the stars, behind the darkness, the galaxy hums softly in many colors, many frequencies, a hidden symphony playing constantly in wavelengths we cannot perceive. There's a giant gamma ray bubble above and below the core, stretching tens of thousands of light years above and below the galactic center. Invisible to our eyes but blazing in gamma rays are two vast ghostly lobes called the Fermi bubbles. They were discovered only recently, in 2010, by NASA's Fermi Gamma Ray Space Telescope, and they came as a complete surprise. These enormous structures extend like twin balloons from the Milky Way's heart, reaching above and below the disk in perfect symmetry. Each bubble spans about 25,000 light-years, roughly the distance from the Sun to the galactic center. They glow in high-energy gamma rays, the most energetic form of light in the universe. No one is entirely sure what caused them. They may be the remnants of a long-ago outburst from the central supermassive black hole, a time when Sagittarius A times was much more active, consuming vast amounts of matter and blasting energy outward in powerful jets. Or they may mark the cumulative effect of intense star formation that once flared through the galactic core, with thousands of supernovae exploding in a relatively short period and driving enormous amounts of hot gas outward. Either way, these enormous structures drift silently over the galaxy, invisible to human eyes but very real. They are reminders that the Milky Way has a past we cannot fully see, a history of violence and energy that left scars stretching across tens of thousands of light years. Echoes of ancient fury, wrapped in gamma ray radiance, hovering above the stars we know. We live in a minor spur between major arms. Our solar system doesn't lie in one of the Milky Way's grand, well-defined spiral arms. We're not in the Perseus arm or the Sagittarius arm or the Scutum Centaurus arm. Instead, we occupy a small, relatively insignificant structure called the Orion Spur, sometimes called the Orion Arm or the Local Arm. It's a minor branch, a relatively quiet lane of stars and gas nestled between the larger Sagittarius and Perseus arms. It's not especially dense compared to the major arms, not especially active. It's a bit of a galactic backwater, really, but that may be precisely why we're here. In the calm between galactic highways, massive supernovae are rarer. Encounters with giant molecular clouds less frequent. Radiation storms from nearby stellar explosions less intense. Gravitational disturbances from passing stars less common. This quiet corner may have given life on Earth the time it needed to emerge and evolve without being constantly disrupted or sterilized by cosmic violence. If we lived in a denser region, closer to the galactic center or deep within a major spiral arm, the night sky might be more spectacular, filled with brilliant nebulae and dense star clusters, but life might also be more precarious, constantly threatened by radiation and gravitational chaos. From the outskirts, from this minor spur, the galaxy seems dramatic and radiant when we look inward. But here, in this quiet corner, far from the center, we found just enough peace and stability for complexity to unfold, for planets to form and remain stable, for life to take root and diversify, for consciousness to emerge and look outward, wondering about its place in the cosmos. Sometimes the best seat in the house is not in the front row, but somewhere in the middle, where you can see everything without being overwhelmed. The Milky Way has a bar-shaped center. When astronomers look toward the galactic core in infrared light, which can penetrate the dust that blocks visible wavelengths, they see not a perfect circular concentration of stars, but a thick elongated bar crossing the middle, a kind of glowing bridge or stripe extending outward from the very center. This bar is made of billions of stars, densely packed, rotating slowly as a coherent structure. It extends perhaps 10,000 to 15,000 light years from the center, though measurements vary. The bar rotates at a different speed than the surrounding disk, creating complex dynamics and gravitational interactions. Bars like this are actually quite common in spiral galaxies. More than half of all spirals show some kind of bar structure. They form when stars in the inner disk begin to drift inward under gravity and pile up along certain stable orbits, creating an elongated concentration. Once formed, the bar becomes self-sustaining, maintained by the collective gravity of all the stars within it. The bar has important effects on the galaxy's evolution. It can funnel gas inward toward the center, feeding the supermassive black hole and triggering bursts of star formation in the core. It also shapes the inner spiral arms, anchoring them and influencing their rotation. The spiral structure we see in the disk is partly a response to the gravitational influence of the central bar. It is not just a shape, not just a visual feature. It's a dynamic engine, actively sculpting the galaxy's heart from within, channeling matter, organizing orbits, and shaping the flow of gas throughout the inner regions. The Milky Way is not a simple spiral. It's a barred spiral with a complex, churning center. Chapter 10, Family Connections. It's part of a larger structure called the local group. The Milky Way doesn't exist in isolation, adrift alone in an empty void. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster bound together by gravity, drifting through space as a coherent unit. The two largest members of this group are the Milky Way and Andromeda, each a massive spiral galaxy with hundreds of billions of stars. They dominate the group like twin giants, each with its own family of smaller satellite galaxies orbiting around it. The Milky Way has dozens of known satellites, including the Magellanic Clouds, the Sagittarius Dwarf, and numerous smaller, fainter dwarf galaxies. Andromeda has a similar retinue. Scattered around these two giants are other members of the group, the Triangulum Galaxy, a smaller spiral that may be loosely associated with Andromeda, numerous dwarf elliptical and irregular galaxies, some so faint they're barely detectable, and perhaps most mysteriously, ultra-faint dwarf galaxies made almost entirely of dark matter, with only a handful of visible stars. The local group spans more than 10 million light-years from edge to edge, though most of its members are concentrated in the space between the Milky Way and Andromeda, which are separated by about 2.5 million light-years. It is bound together not by proximity alone, but by gravity. The members of this group share a common motion through space, influenced by each other's gravitational pull and by the larger structures beyond. We are part of a family, quiet, widely spaced, but still linked by invisible threads of shared motion and mutual attraction. Galaxies in the local group are gravitationally bound. Despite their vast separations, despite the millions of light years between them, the galaxies of the local group are not drifting apart. In fact, many are moving slowly toward one another. Gravity holds them in a kind of slow-motion dance, curving their paths across millions and billions of years. Some of the smallest galaxies orbit the Milky Way like moons around a planet, looping and falling, dissolving into streams as tidal forces tear them apart. The Sagittarius dwarf is a perfect example, orbiting the Milky Way and being slowly unraveled with each pass, its stars smeared across the sky in long tidal tails. Others drift more independently but remain tethered to the group, caught in a web of shared motion. Andromeda and the Milky Way are approaching each other. As we've discussed, the Triangulum galaxy may be orbiting Andromeda, though its exact motion is still being studied. Even the smallest dwarfs, faint and sparse, are held within the group's gravitational embrace. Over time, billions of years into the future, this group may condense further. Galaxies may merge, collide, or be absorbed. The structure we see today is not permanent. It's a snapshot of an ongoing process, a family portrait frozen in time while the members continue to drift, drawn closer by time, inertia, and the long reach of gravity. Eventually, perhaps, the local group will become a single massive galaxy, a merger of all its members. But that's many billions of years away, long after our sun has died. The galaxy's disk has a thick and thin component. The Milky Way's disk looks flat from a distance, a neat plane of stars and gas stretching across tens of thousands of light years. But up close, when you examine it carefully, it's layered. It has structure and depth. The thin disk is where we live. It's a wide, dense plane filled with young stars, open clusters, massive O and B stars, and active star-forming regions. It's only about 1,000 light-years thick, relatively speaking, and it contains most of the galaxy's gas and dust. This is the disk you see when you look at pictures of spiral galaxies, the bright, well-defined plane that glows with starlight. But above and below it lies the thick disk, older, puffier, and more diffuse. It extends several thousand light-years above and below the thin disk, and it contains older stars with fewer heavy elements. These stars tend to move on orbits that are more tilted, more elliptical, suggesting they formed under different conditions or were stirred by early galactic collisions and mergers. The thick disk may represent an earlier phase of the galaxy's evolution, before the structure settled into the neat, flat, thin disk we see today. Or it may have been puffed up by ancient mergers, by dwarf galaxies crashing through the disk and scattering stars vertically. The exact origin is still debated, but its existence is clear. The galaxy's disk is not uniform or monolithic. It's textured, layered, and shaped by billions of years of history. Like sediment settled on the floor of a cosmic ocean, layer upon layer, each telling a story. The galaxy's magnetic field threads through the disk. Though invisible to the eye, invisible even to most instruments, the Milky Way is laced with a vast magnetic field stretching across the disk, rising into the halo. and weaving through the interstellar medium like invisible currents in an ocean. This field is weak by earthly standards, thousands of times weaker than the magnetic field you'd feel from a refrigerator magnet. But over galactic distances, stretched across light years and tens of thousands of light years, it has profound effects. It shapes how cosmic rays travel through the galaxy, channeling and deflecting them. It influences how gas clouds collapse and where they fragment. It affects the motion of charged particles in the interstellar medium. The magnetic field aligns roughly with the spiral arms in some regions, following the curves of the disk. In other places, it forms arcs above the plane, loops and bubbles carved out by supernova explosions and stellar winds. Near the galactic center, the field becomes more chaotic, tangled and twisted by the complex dynamics of that crowded region. Studying this magnetic field requires specialized techniques. Radio telescopes can detect the faint polarization of starlight caused by aligned dust grains, which tend to orient themselves along magnetic field lines. They can also observe synchrotron radiation, light emitted by electrons spiraling along magnetic fields at high speeds. The Milky Way does not just glow with light and mass, it breathes with magnetism, a subtle pulse running through its bones, shaping the flow of matter and energy in ways we're only beginning to understand. Chapter 11, The Space Between. The interstellar medium is full of invisible structures. Between the stars lies more than emptiness, more than vacuum. The interstellar medium, a thin blend of gas, dust, plasma, and magnetic fields, weaves its way through the Milky Way like a cosmic fog. To the naked eye, it is mostly invisible, contributing only faint glows in certain regions. But when viewed with radio telescopes, infrared instruments, and X-ray observatories, it reveals stunning complexity. It forms long filaments where gas is compressed by magnetic fields. It creates bubbles and cavities carved out by stellar winds and supernova explosions. It shows shock waves rippling through space at thousands of kilometers per second, compressing and heating the gas as they pass. And it harbors cold, dense clouds where stars are born, regions so dark and opaque they appear as black voids against the starry background. The interstellar medium is not a void or a blank canvas. It's a shifting web of matter and magnetism, constantly stirred by stellar winds, shaped by explosions, compressed by shock waves, and enriched by the deaths of stars. It's the connective tissue of the galaxy, the medium through which energy and matter flow, the substrate from which new stars and planets emerge. The space between stars is not empty. It's alive with structure, with motion, with complexity that rivals the stars themselves. Cosmic rays constantly pass through us from the galaxy. Every second, high-energy particles, mostly protons and atomic nuclei, stream through your body. They pass through the walls of your house, through the atmosphere, through the Earth itself. These are cosmic rays, and they are everywhere, filling the galaxy with a constant background drizzle of energetic particles. Most cosmic rays are launched by supernova explosions. When a massive star explodes, it doesn't just scatter gas and heavy elements into space. It also accelerates particles to enormous energies, close to the speed of light, through complex interactions with magnetic fields and shock waves. These particles then propagate through the galaxy, bouncing off magnetic field lines, scattered by clouds, traveling for millions of years before eventually colliding with something. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles, cascading down through the air in a brilliant display that's invisible to our eyes but detectable with specialized instruments. Most of the time, we don't notice them. They pass harmlessly through our bodies, leaving no trace. Occasionally, one might interact with an atom in our cells, but the effect is usually negligible compared to other sources of radiation we encounter daily. But they carry stories. Each cosmic ray is evidence of an ancient supernova, a trace of distant acceleration, a message from the violent hearts of dying stars. Even as you rest here, drifting towards sleep, the galaxy is whispering to you in particles, in silence, in lightless rays that speak of creation and destruction happening far away. The galaxy is not symmetrical. Though many diagrams show the Milky Way as a neat, even spiral with perfectly balanced arms, the reality is messier. The galaxy is not perfectly symmetrical. One side of the disk appears thicker than the other. Some spiral arms are brighter, longer, or more tightly wound. Others fade into fragments or split unexpectedly. The warp in the outer disk is lopsided, bending more on one side than the other. Even the star counts between different hemispheres are slightly off, suggesting an uneven distribution of mass. The central bar is not perfectly aligned with the rotation axis, and the halo, studied in detail by surveys like Gaia, shows complex substructure, streams and clumps that hint at past mergers and ongoing disruptions. These asymmetries may be caused by gravitational encounters with dwarf galaxies, especially the Magellanic Clouds, which are massive enough to pull on the Milky Way's edges and create tidal distortions. They may also be influenced by dark matter clumps in the halo or by the lingering effects of ancient collisions that haven't fully settled. Galaxies, like living things, carry traces of their histories in their shapes, scars of collisions, wrinkles of time, quirks of uneven growth that give them character and depth. The Milky Way is not a perfect geometric object. It's a living structure, shaped by forces both seen and unseen, carrying the marks of its long, complex past, and in that imperfection lies a kind of beauty. The oldest known star may live in our halo, high above the galactic plane, drifting through the halo in a long, lonely orbit. Astronomers discovered a star that may be nearly as old as the universe itself. It's called SMSS J031300, 36 to 670,839.3, though some refer to it simply as SM0313, and its composition is extraordinary. It contains almost no heavy elements, less iron than any other star ever observed, only about 1/10,000,000th the iron content of the Sun. This is a signature of stars born in the universe's first few 100 million years, shortly after the Big Bang, before generations of supernovae had enriched the cosmos with heavy elements. This star likely formed over 13 billion years ago, when the universe was still young and wild, when the first galaxies were just beginning to assemble from dark matter and primordial gas. It has been burning quietly ever since, a low-mass red dwarf that will continue to shine for trillions of years, long after more massive stars have exhausted their fuel and died. It is not just a star, it is a time capsule, a living relic from the universe's earliest dawn, somehow preserved through billions of years of galactic evolution, mergers, and change. In its light, faint and red as it is, we see not the galaxy as it is now, but as it was in its infancy. We see the beginning, still glowing softly in the present. The center of the galaxy spins faster than the outskirts. In the inner regions of the Milky Way, packed with stars and gas and dark matter, the gravitational pull is intense. Near the core, stars orbit the center much more rapidly than those farther out, some complete revolutions in just a few million years, racing through their orbits at thousands of kilometers per second. Out in the suburbs of the galaxy, like where our sun lives, about 26,000 light-years from the center, stars orbit more slowly. It takes us 225 million years to complete one circuit, and farther still, in the outermost reaches, the orbital speeds remain roughly constant rather than dropping off as you'd expect from Newtonian mechanics. This creates a differential rotation, a twisting pattern where the inner galaxy spins faster than the outer regions. If you could watch the Milky Way evolve over millions of years in a time lapse, you'd see the spiral arms stretching and shearing, wrapping tighter around the center while the outer edges lag behind. This uneven rotation is one of the reasons spiral arms exist and persist. The density waves that create them are sustained by this differential rotation, by the complex interplay of gravity, motion, and resonance that keeps the pattern stable even as individual stars drift through them. The galaxy moves like a great wheel, but one whose rim lags behind its core, creating beautiful, swirling patterns in the disk. Chapter 12. Births and Deaths. Stars are born from cold, collapsing gas. In the dark, quiet arms of the Milky Way, far from the bright lights of existing stars, star formation begins in silence and cold. Massive clouds of molecular hydrogen, sometimes hundreds of light years wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, shielded from starlight and cosmic radiation, gravity slowly takes hold. Small regions within the cloud grow denser, perhaps triggered by a passing shock wave from a supernova, or by the compression of a spiral arm, or simply by random fluctuations in density. As gas accumulates, the region begins to collapse under its own weight. As it falls inward, it heats up, releasing gravitational potential energy. It spins faster, conserving angular momentum. It flattens into a rotating disk. At the center of this collapsing region, a protostar forms, a glowing core of hot gas, not yet dense or hot enough for fusion, but growing, accumulating mass, heating up with each passing year. Around it, the disk of gas and dust will eventually form planets, moons, asteroids, and comets, but that comes later. For now, the protostar continues to grow, drawing in material from its surroundings. Eventually, after perhaps a few 100,000 years, the core reaches the critical temperature and density needed for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. The star ignites, blazing with its own light for the first time. From the coldest shadows come the brightest lights, spun gently into being by the quiet force of gravity. It's a process that has been repeating for billions of years, in cloud after cloud, across the entire galaxy. And it continues even now, as you lie here in the dark, drifting towards sleep. New stars are being born. Somewhere in the Milky Way, right now, a protostar is igniting for the first time. Star clusters can dissolve into the galactic field. Many stars are born not in isolation but in groups, in tight clusters formed from the same collapsing gas cloud. These clusters, bound by mutual gravity, drift together through the galaxy for millions or even billions of years, families of stars moving as one. But over time, these clusters begin to scatter. Tidal forces from the Milky Way's overall gravitational field pull on the cluster, stretching it, distorting it. Close encounters with other stars or with giant molecular clouds can strip away members. Internal dynamics, the three-body interactions between stars within the cluster, can eject members at high velocities. Stars peel away one by one, drifting off into the general star field of the galaxy. The cluster loses mass, becomes less tightly bound, and eventually dissolves entirely. Its stars scatter across the disk, indistinguishable from the rest, carrying only faint chemical signatures that hint at their common origin. Even our sun was likely born in such a cluster long ago, some 4.6 billion years ago. Its siblings, dozens or hundreds or perhaps thousands of stars that formed from the same cloud, have long since scattered. They're out there somewhere, moving on their own orbits, shining in distant parts of the galaxy. We might never find them, but they exist, carrying faint traces of our shared beginning. The galaxy contains ancient hyper-metal poor stars. Among the rarest and most precious objects in the Milky Way are what astronomers call hypermetal poor stars. These are stars whose atmospheres contain almost no elements heavier than helium. Some contain less than 1/10,000th the iron found in the Sun. A few contain even less, barely detectable traces. These stars are believed to be among the first born after the very first supernovae in the universe's history. The first generation of stars, born from purely primordial gas, contained no metals at all. When they exploded as supernovae, they scattered tiny amounts of heavy elements into the surrounding gas. The next generation of stars, forming from this slightly enriched material, would have these hyper-low metal abundances. Finding these stars is like finding needles in a cosmic haystack. They're rare, faint, scattered throughout the halo, but each one is a kind of relic, a living connection to the earliest epochs of star formation, carrying only faint traces of enrichment from a universe still forming itself. They are incredibly old, often 12 or 13 billion years old, nearly as ancient as the universe, and their glowing, gravitationally bound signatures from a near-forgotten epoch, from a time before the Milky Way existed in its current form, when the cosmos was younger and wilder. In their light, we see the beginning, not metaphorically, but literally. We see light from a star that has been shining since shortly after the Big Bang. Planetary systems form throughout the Milky Way. Planets are not rare, or special, or unusual. They are a natural consequence of star formation, an inevitable byproduct of the process that creates new suns. As a new star ignites at the center of a rotating disk of gas and dust, the material in that disk doesn't simply fall into the star. Much of it remains in orbit, gradually sticking together through collisions and gravitational attraction. Dust grains collide and merge. Pebbles form, then boulders, then planetesimals kilometers across. These continue to collide and grow, eventually forming planets. Rocky planets form in the inner regions where it's warm enough for silicates and metals to condense. Gas giants form farther out where it's cold enough for ices to exist and where there's more material available. Ice giants form at intermediate distances. Debris left over becomes asteroids and comets. Across the Milky Way, planetary systems are common, incredibly common. Surveys like Kepler and TESS have found thousands of exoplanets, and statistical analysis suggests that nearly every star in the galaxy hosts at least one planet. Some systems are vast, with multiple gas giants and frozen moons orbiting far from their star. Others are compact, with several rocky planets huddled close to dim red dwarfs. Some may resemble our own solar system. Others defy our expectations entirely, with hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. The galaxy is not just full of stars, it's full of worlds, solar families, systems, each one with its own unique balance, its own configuration of orbits, its own history and potential. Somewhere out there, on one of those distant worlds, under a different sun, life may be looking up at the stars and wondering if they're alone. They're not. Neither are we. Earth is near the co-rotation radius. In the Milky Way, the spiral arms rotate at a different speed than individual stars. The arms are patterns, density waves that move through the disk at their own pace, slower than most stars. But there is a special distance from the galactic center called the co-rotation radius, where the average orbital speed of stars matches the rotation speed of the spiral arms themselves. Earth's sun orbits close to this boundary, not exactly on it, but near enough that we don't cross through spiral arms very frequently. We spend most of our time drifting through the relatively quiet spaces between arms, only occasionally passing through the denser regions where star formation is more active and supernova more common. This gentle match in motion may have helped shield Earth from some of the galaxy's more violent phenomena. Spiral arms contain more massive stars, which means more supernovae. More supernova means more radiation, more cosmic rays, more potential disruptions to planetary atmospheres and biospheres. By living near the co-rotation radius in a more stable neighborhood, Earth may have avoided the worst of these disturbances. We live, quite possibly, in one of the safer regions of the galaxy, not shielded by walls or barriers, but by resonance, by a fortunate match between our orbital motion and the rotation of the galaxy's structure. It's subtle, almost coincidental, but it may have mattered for the emergence and survival of life. Sometimes the best place to be is not the most dramatic or the most active, but the place that offers just enough stability for complexity to unfold. The sun bobs up and down through the galactic plane. As it orbits the Milky Way, the sun doesn't follow a perfectly flat path confined to the galactic plane. Instead, it moves in a gentle wave, a vertical oscillation that carries it above and below the midplane of the disk over tens of millions of years. This motion is caused by the gravitational pull of the galaxy's mass. As the sun drifts above the plane, the collective gravity of all the stars and dark matter below pulls it back down. It passes through the plane, overshoots to the other side, slows, stops, and then falls back again. It's like a weight bobbing on a spring, oscillating up and down in a slow, regular rhythm. The period of this oscillation is roughly 60 to 70 million years, and the amplitude is about 200 to 300 light years above and below the plane. Right now, we're moving upward, climbing slowly through the northern edge of the disk. Some researchers have wondered whether this vertical motion might influence cycles of extinction on Earth. The idea is that as we pass through the densest part of the galactic plane, we might encounter more dust, more comets, more gravitational perturbations that could send objects from the outer solar system inward, potentially causing impacts. The evidence for this is not yet clear, and the hypothesis remains speculative. But it's a reminder that even on its steady path around the center, the sun is not gliding smoothly. It's swaying softly through space, rising and falling in a gentle cosmic dance that plays out over millions of years. Chapter 13, The Invisible Foundation. We don't know what dark matter is, but we know it's there. Dark matter makes up most of the Milky Way's mass, perhaps 85% or more of the total. Yet it has never been seen directly. It does not emit light, it does not absorb light, it does not reflect or scatter light. It passes through ordinary matter as if both were ghosts, interacting only through gravity. But its gravitational effects are unmistakable and profound. It holds the galaxy together, providing the mass needed to explain the rotation speeds of stars in the outer disk. It shapes the formation of large-scale cosmic structures, helping galaxies form and cluster, and it affects the motion of satellite galaxies, bending their orbits, holding them captive in the Milky Way's halo. Without dark matter, the Milky Way would fly apart. The outer stars, moving too fast for the visible mass to hold them, would be flung into intergalactic space. The galaxy would unravel, scattering into the void within a few 100 million years. We detect dark matter not by seeing it, but by watching how it moves other things, by tracking the orbits of stars, by measuring the rotation curve of the galaxy, by observing how light from distant galaxies is bent by intervening dark matter, a phenomenon called gravitational lensing. Astronomers have proposed many theories about what dark matter might be. Exotic particles like WIMPs or axions that barely interact with ordinary matter, primordial black holes formed in the early universe, or something entirely unexpected, a form of matter fundamentally different from anything we've encountered. Decades of experiments have tried to detect dark matter particles directly, deep underground in mines and laboratories, shielded from cosmic rays. So far, none have succeeded. The mystery remains. Dark matter is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest mysteries in science. We live within its embrace, held together by forces we cannot see, shaped by matter we cannot touch, There's more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat, luminous disk, that bright plane of light stretching across tens of thousands of light years. But the majority of the galaxy's mass resides elsewhere, in the dark matter halo. This halo extends far beyond the furthest stars, perhaps 500,000 light years or more, from the center, 10 times the radius of the visible disk. It's spherical or slightly elliptical, surrounding the entire galaxy like an enormous invisible bubble, and it outweighs the disk by a large margin, perhaps by a factor of 10 or more. The halo is populated sparsely with ancient stars and globular clusters, but its true bulk is unseen dark matter. This is what holds the galaxy together, what provides the gravitational glue that keeps everything bound despite the high velocities of stars in the outer regions. When we think of the Milky Way, we picture its spiral arms and starry plane. That's what we see in photographs, what captures our imagination. But that's only the glowing surface, the visible tip of a much larger structure. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. The Milky Way's core may have flared as a quasar. Today, the heart of our galaxy appears quiet, almost dormant. The supermassive black hole at the center consumes only small amounts of material, producing occasional flares but nothing sustained or dramatic. But there is evidence that it was once much more active, burning with incredible brilliance. The presence of huge gamma-ray structures like the Fermi bubbles, along with traces of high-energy light reflected in surrounding gas clouds, suggests that Sagittarius A times may have once flared as a quasar. A brilliant, violent beacon fueled by torrents of infalling matter, shining with the light of billions of suns. Quasars are among the brightest objects in the universe, powered by supermassive black holes consuming vast amounts of gas and dust. Material spirals inward in a glowing accretion disk, heated to millions of degrees, radiating across the entire electromagnetic spectrum. Jets of matter and energy can be blasted outward at nearly the speed of light, extending for thousands of light years. If the Milky Way once burned like this, perhaps a few million or a few billion years ago, it would have looked dramatically different. A spiral wrapped around a blinding heart of light, outshining all the stars in the disk combined. The radiation would have flooded the inner galaxy, ionizing gas, stripping atmospheres from planets too close, reshaping the structure of the core. That time is past. The black hole is quieted. Its fuel supply dwindled, but the echoes remain, written in gamma rays and reflected light in structures carved by ancient energy. The Milky Way has a violent past, a history of brilliance we can only glimpse in the traces left behind. The galaxy's structure changes over billions of years. Galaxies may look timeless in photographs, frozen and unchanging, but they are always evolving, always in motion, always transforming. Spiral arms shift and reorganize. Bars form and dissolve over billions of years. Gas flows inward and outward, redistributing mass. Stars are born and die, leaving behind remnants that alter the chemical composition and dynamics of the interstellar medium. Even the shape of the Milky Way's disk, warped and rippling and lopsided, is slowly changing. Encounters with dwarf galaxies bend and twist the structure, creating waves that propagate through the disk over millions of years. Dark matter clumps in the halo can perturb the orbits of stars. Ancient mergers continue to leave their mark, streams of stars settling into new configurations. Over billions of years, the galaxy's silhouette has shifted, morphed, transformed. The Milky Way of today is not the one that existed 10 billion years ago, when it was smaller, more chaotic, actively merging with larger companions. And it's not the one that will exist 10 billion years from now, when it may have merged with Andromeda and become something entirely different. The galaxy's beauty lies not in permanence, but in quiet transformation. It is not a fixed object, but a living structure, shaped by forces both seen and unseen, carrying forward through time, always becoming something new. Chapter 14. Waves in Space-Time. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide. Black holes spiral together and merge. Neutron stars crash in brilliant kilinovae. Entire galaxies interpenetrate and combine. These events send out gravitational waves, ripples in the very fabric of space-time itself, traveling outward at the speed of light. Though incredibly faint by the time they reach us, some of these waves pass through the Milky Way, through the solar system, through the Earth, through your body, distorting space by tiny, almost immeasurably small amounts as they travel. They stretch and squeeze space-time, but so gently that even our most sensitive instruments can barely detect them. Observatories like LIGO and Virgo have captured several of these waves, detecting the merger of black holes and neutron stars billions of light years away. Each detection is a triumph, a confirmation that space-time is not rigid, but flexible, dynamic, shaped by mass and energy. New experiments aim to detect the background hum of gravitational waves that fills the cosmos, a constant noise generated by countless mergers and violent events throughout the history of the universe. Even now, as you rest here, space itself is shifting around you. Not enough to feel, not enough to notice, but enough to tell us that somewhere far away, something massive and dramatic is happening. The universe is not silent. It rings with gravitational waves, with the echoes of cosmic violence, with the songs of merging black holes that we've only just learned to hear. Some stars orbit in elongated, tilted paths. Not all stars move in neat circles around the galactic center. Some follow long, stretched ellipses, their orbits carrying them high above and far below the disk, tilted at odd angles from the main plane. These stars loop outward into the halo, spend millions of years in the sparse outer regions, then fall back down toward the disk, passing through it before climbing back out on the other side. These unusual orbits are clues, three-dimensional maps of the galaxy's chaotic past. Stars on such paths likely come from different origins. They may be relics of dwarf galaxies swallowed by the Milky Way, retaining the orbital characteristics of their original systems. They may be survivors of ancient gravitational upheavals, encounters that flung them onto these extreme trajectories. By tracing their motion, by measuring their velocities and chemical compositions, astronomers can reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems, tilted and stretched, but still bound to the whole, still orbiting the center, still part of the galaxy even though they spend most of their time far from the disk. They are wanderers, exiles, perhaps, but they carry stories of the galaxy's violent history, written in their motion. The Milky Way emits neutrinos we can barely detect. Every second, trillions upon trillions of neutrinos pass through your body. They come from the sun, from supernova remnants, from cosmic rays striking atoms in the atmosphere, from nuclear reactions deep within the Earth. They come from across the Milky Way and beyond. The galaxy is bathed in them, yet neutrinos are so light, so weakly interacting, that they slip through almost everything, leaving no trace. They can pass through the entire Earth as if it were transparent. They can travel for billions of light years without ever colliding with anything. Detecting them requires special observatories buried deep underground or under ice, shielded from cosmic rays and other background radiation. Even then, only a tiny fraction of the neutrinos passing through are ever caught. When one does interact with an atom, it produces a flash of light, a brief spark that detectors can capture. Each detection is rare and precious. Neutrinos carry information from places we cannot see any other way, from the cores of stars where fusion happens, from collapsing giants on the verge of supernova, from the galactic center where mysterious processes unfold. They are messengers from the hidden universe, from regions too dense or too distant for light to escape. They are the whispers of cosmic fire, passing silently through the galaxy, through space, through you, carrying secrets from the heart of creation. Interstellar space isn't empty, it's a turbulent sea. Between the stars, space is not smooth or still or uniform. The interstellar medium, that thin soup of gas and dust, is stirred constantly by shock waves from supernova, by stellar winds from massive stars, by magnetic fields threading through it, by the motion of stars and clouds. Temperature can vary wildly across short distances. Some regions are heated to millions of degrees by recent explosions, glowing in X-rays. Others are chilled to just a few degrees above absolute zero, so cold that molecules can survive and complex chemistry can occur. Flows of material collide and mix. Clouds stretch and fold and tumble. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Vortices and eddies form. Shock fronts propagate. Density fluctuations trigger new star formation or disrupt existing structures. Star formation, cosmic ray propagation, the distribution of heavy elements, even the evolution of the galaxy as a whole, are all affected by this restless sea. What looks from afar like calm starlight is, up close, a dynamic, rippling fabric shaped by invisible winds and ancient energy. The space between stars is not empty. It's alive, with motion, with structure, with forces that shape the galaxy's destiny. Chapter 15, Orphans and Wanderers. The galactic halo may contain rogue planets. Planets are not always tethered to stars. Some form normally in the disks around young stars, but are later ejected from their systems by gravitational interactions. A close encounter with another planet, a passing star, or a three-body dance that flings one planet outward while stabilizing the others. Other rogue planets may never have had a star at all, forming independently in collapsing gas clouds, too small to ignite fusion but massive enough to pull themselves together. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Without a star to warm them, their surfaces freeze. Any atmospheres they once had may have condensed and fallen to the ground as snow, but deep inside, some may still have internal heat from radioactive decay, keeping liquid oceans beneath thick ice crusts hidden from the cold of space. Though difficult to detect because they emit no light of their own, studies suggest there may be billions of them in the Milky Way, perhaps even more rogue planets than stars. Some drift through the disk, others wander in the outer halo, where stars are few and far between. Without light or warmth from a sun, they float unseen, moving silently through the darkness. They are orphans of the galaxy, planetary drifters following long, lonely paths through the space between stars. Some may wander for billions of years without ever coming close to another object. They are reminders that not every world has a home. Not every planet circles a star. Magnetic fields shape the flow of cosmic dust. Interstellar dust, those tiny grains of carbon and silicates and ices, moves not just under the influence of gravity. It's also shaped by the galaxy's magnetic field, by radiation pressure from stars, by the flow of gas in the interstellar medium. These magnetic fields thread through the galaxy like invisible currents, guiding the motion of charged particles and influencing how dust aligns and moves. In some regions, dust grains spin rapidly, heated by starlight or collisions, emitting faint microwave radiation. In others, they align with magnetic field lines, causing the starlight passing through them to become polarized. Understanding these effects helps astronomers trace the structure of the magnetic field, map its strength and direction, and even remove its influence from observations of the cosmic microwave background The faint afterglow of the Big Bang. Dust is not passive. It doesn't just drift randomly through space. It dances to a magnetic rhythm, falling into hidden patterns shaped by invisible forces. It responds to fields we cannot see, creating structures and alignments that reveal the galaxy's electromagnetic skeleton. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent and spectacular events in the universe, a kilonova. In this brief, blinding explosion lasting only a few days, enormous quantities of heavy elements are forged through a process called rapid neutron capture. Gold, platinum, uranium, rare earth elements, all the heaviest atoms in the periodic table, too heavy to be created even in supernova explosions, are forged in these collisions. The intense neutron flux allows atoms to capture neutron after neutron, building up to the heaviest elements before decaying into stable forms. These materials are cast into space, mixing with the interstellar medium, eventually being incorporated into new generations of stars and planets. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from neutron star mergers. They are not just luminous bodies. They are record keepers of ancient cataclysms, burning with the residue of stellar collisions, carrying in their light the evidence of some of the most extreme physics in the universe. The golden jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was forged in neutron star collisions, scattered into space, and eventually gathered into planets like Earth. We wear the remnants of cosmic violence on our fingers. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies the central bar, that elongated structure of stars crossing the core. But deep within that bar, hidden by dust and distance, astronomers have found hints of another structure, a smaller, secondary bar tilted at a different angle, rotating independently. This inner bar, sometimes called a nuclear bar, is difficult to observe directly. It's buried deep in the galactic center, obscured by gas and dust, but its gravitational influence appears in the motion of nearby stars and gas clouds, in the way material flows through the core. Bars like this may help funnel material toward the supermassive black hole, feeding it and potentially triggering periods of increased activity. They may also influence the formation of stars in the core, organizing the flow of gas into specific patterns. The Milky Way's center is not one simple structure. It's layered, nested, complex, a bar within a bar, structures rotating at different speeds, each influencing the other, creating a dynamic, ever-shifting core that we're only beginning to understand. The heart of the galaxy is like a cosmic clockwork, gears within gears, all turning together. Chapter 16. Cosmic Rivers. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system, isolated and self-sufficient. It draws in fresh gas from the intergalactic medium, from the vast cosmic web that connects all galaxies across the universe. Long, tenuous streams flow inward, pulled by gravity, feeding the galaxy with raw material for new stars. These inflows provide the fuel that keeps star formation going, replenishing what the galaxy loses over time through stellar winds, supernova ejecta, and other outflows. Without these inflows, the Milky Way would have exhausted its gas supply billions of years ago and would now be a dim, dying collection of aging stars. Some gas arrives as cold filaments, slipping quietly into the disk, barely detectable except in specialized surveys. Other streams fall in hot, shock-heated by their journey through the intergalactic medium, glowing in ultraviolet and X-ray wavelengths. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond, to the cosmic web that shaped the distribution of matter throughout the cosmos. Even now, The Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early universe, maintaining its vibrancy, ensuring its future. Hot gas bubbles form chimneys out of the disk. When clusters of massive stars form and evolve together, their combined stellar winds and eventual supernova explosions create enormous cavities in the interstellar medium. These bubbles, filled with hot gas heated to millions of degrees, expand outward, pushing aside the cooler, denser gas. Sometimes multiple bubbles merge, forming superbubbles that can span hundreds of light years. If these grow large enough, they can punch through the thin disk entirely, creating chimneys or channels that vent hot gas upward into the halo. The result is a kind of galactic chimney, a pathway where energy, gas, and magnetic fields escape from the dense plane of the galaxy, flowing outward into the more diffuse halo. These chimneys regulate the pressure of the interstellar medium, redistribute heavy elements from star formation regions into the halo, and help shape the overall structure of the galaxy. The galaxy, in this way, breathes, not just within the disk, but through towering columns that carry its energy and matter up and out into the dark, connecting the disk to the halo in a grand circulation of material. The galaxy shines in X-rays from old stars and black holes. Though the Milky Way appears calm and gentle in visible light, it glows fiercely in X-rays, revealing a hidden realm of extreme temperatures and violent processes. X-rays pour from the galactic core, from the regions around Sagittarius A times, where gas is heated to millions of degrees before falling into the black hole. They come from white dwarfs in binary systems, where matter stripped from a companion star spirals down onto the dense stellar remnant, heating up and radiating X-rays. They come from neutron stars doing the same thing, pulling gas from orbiting companions and glowing brilliantly in high-energy wavelengths. Hot gas in the halo, heated by supernova explosions and outflows from the disk, also emits faint X-rays, revealing the galaxy's larger skeletal structure, the framework that supports everything we see. We cannot perceive this high-energy light with our eyes, but telescopes like Chandra and XMM Newton paint a very different portrait of the galaxy. Not a tranquil spiral of starlight, but a realm of extreme temperatures, compact remnants, and hidden radiation, a galaxy that burns with invisible fire. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning incredibly fast, rotating dozens or even hundreds of times per second. If the magnetic field is aligned just right, beams of radiation sweep across space like a lighthouse, and if Earth happens to lie in the path of one of these beams, we detect regular pulses. These are pulsars. Some pulsars are so consistent, so regular in their timing, that they rival atomic clocks in precision. They rotate with almost perfect steadiness, pulsing with millisecond accuracy. Astronomers use them as cosmic timekeepers, tracking their signals to measure distances across the galaxy, to test theories of gravity, and even to search for gravitational waves by looking for tiny timing anomalies caused by space-time distortions. Across the Milky Way, pulsars blink quietly in the dark, remnants of stellar death, yes, but also beacons of astonishing order and regularity. They keep time not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. They are the galaxy's clocks, wounded by catastrophe, running with almost perfect precision. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in the wavelengths our eyes can see, hidden by dust, distance, or simply the faintness of the light. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas distributed throughout the disk, the raw material for star formation. They outline magnetic fields through synchrotron radiation, light emitted by electrons spiraling along field lines at high speeds. They highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy whose radio waves pass through the Milky Way's structure, giving us information about the intervening material. Using arrays of radio telescopes working together, astronomers have mapped the spiral arms, measured the warp of the disk, discovered star-forming regions cloaked in darkness, and traced the distribution of matter throughout the galaxy. Where visible light is blocked, where infrared fades, radio waves let us see. The galaxy speaks in a language we can't hear with our ears. But science has learned to translate it into maps and images, into shape and shadow, revealing the hidden architecture of our cosmic home. Chapter 17. Scattered Family. The sun was likely born in a stellar cluster. Stars rarely form in solitude. They're usually born in groups, sometimes hundreds or thousands at a time, all condensing from the same giant molecular cloud. Our sun was almost certainly one of these, part of a stellar cluster that formed about 4.6 billion years ago. For a while, perhaps a few million or tens of millions of years, the sun and its siblings drifted together, bound by mutual gravity, moving through the galaxy as a family. But over time, gravitational tides from the Milky Way, close encounters with other stars, and the internal dynamics of the cluster itself caused it to dissolve. Stars peeled away one by one, flung outward by gravitational interactions, or simply drifting apart as the cluster's cohesion weakened. Eventually, the cluster scattered completely, its members dispersing across the galaxy, each following its own independent orbit. Most of the sun's siblings have wandered far by now, tens of thousands of light years away, carrying with them faint memories of a shared beginning. Some may still shine nearby, but we wouldn't recognize them easily. They've been separated for billions of years, their orbits diverged, their paths through the galaxy completely different from ours. The sun's siblings are scattered across the galaxy. Though the sun's birth cluster dissolved long ago, astronomers are searching for its lost siblings, stars that share the sun's age, motion, and chemical fingerprint. Stars that were born from the same cloud of enriched gas, carrying the same mix of elements, the same isotopic ratios, the same subtle signatures. Using vast surveys like Gaia, which has measured the positions and motions of over 1 billion stars, and spectroscopic databases that analyze the chemical composition of millions, researchers hope to identify these long-lost relatives. A few candidates have emerged, stars with similar ages and compositions, moving on orbits that, when traced backward through time, intersect with the sun's probable birth location. But confirming these connections is difficult. After 4.6 billion years of orbital motion, of gravitational perturbations, of close encounters with molecular clouds and other stars, the trail has grown cold. Still, the search continues. If found, these sibling stars could reveal details about the conditions in which the sun and the early solar system were born. They could tell us about the environment, the gas cloud, the nearby supernova that might have triggered the collapse, the chemistry that seeded our solar system with the elements needed for rocky planets and life. Our place in the galaxy is not entirely solitary. Somewhere out there, the sun's ancient kin may still shine, scattered across the disk, each one carrying a fragment of our shared origin. Chapter 18. Motion and Memory. The galactic disk wobbles as it spins. The Milky Way's disk is not perfectly flat and stable. It wobbles gently, rippling like a spinning plate that's been nudged slightly off balance. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other, creating a graceful S-curve when viewed edge-on. This warping may be caused by the gravitational influence of nearby satellite galaxies, especially the Magellanic Clouds, which are massive enough to tug on the Milky Way's edges as they orbit. It might also be influenced by dark matter clumps in the halo or by the lingering effects of past mergers that haven't fully settled. The wobble itself rotates slowly, like a wave moving through the disk, completing one full cycle over hundreds of millions of years. From Earth, embedded within the disk, we don't feel or perceive this motion. But from afar, if you could step outside the galaxy and watch it over time, the Milky Way would look like it's dancing slowly through space, its edges rising and falling in a gentle cosmic rhythm. Galactic tides can distort star clusters and streams, just as the moon's gravity pulls tides on Earth, raising and lowering the oceans. The immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters feel this pull. Satellite galaxies feel it. Globular clusters, gas clouds, even individual stars can be affected. Over time, these tides stretch and distort structures. A star cluster orbiting through the galaxy experiences stronger gravitational pull on its near side than on its far side. This differential force stretches the cluster, pulling stars away from the edges, gradually unraveling it. Many of the faint arcs and streams of stars mapped across the sky are remnants of such encounters. Clusters and dwarf galaxies in the process of being torn apart, their stars smeared across space in long tidal tails that trace their former orbits. The galaxy doesn't break these structures suddenly or violently. It unravels them patiently, gently, strand by strand over millions and billions of years. A slow, inexorable dismantling driven by gravity's patient hand. The Milky Way's mass is still uncertain. You might think we would know the mass of our own galaxy with precision, but measuring it is remarkably difficult and estimates vary considerably. Stars and gas make up only a small portion of the total mass. The rest lies in the dark matter halo, which we cannot see or measure directly. Current estimates suggest a total mass somewhere between 1 and 2 trillion times the mass of the Sun, but the uncertainty range is large. The problem comes from trying to measure how fast stars and satellite galaxies orbit at great distances from the center, where dark matter dominates. Different methods give different results. Measuring the velocities of satellite galaxies suggests one mass. Modeling the rotation curve gives another. Tracking stellar streams provides a third estimate. Reconciling these measurements is an ongoing challenge. The Milky Way is our home, the galaxy we've studied longer and more thoroughly than any other. And yet its weight, its total gravitational pull, remains a quiet mystery. One more reminder that even the familiar can hold surprises. It may be heavier than Andromeda. For many years, astronomers assumed that Andromeda, slightly larger in diameter and appearing brighter, was also more massive than the Milky Way. It seemed logical. But recent measurements suggest that assumption may be wrong. Analysis of the Milky Way's dark matter halo, based on the motions of distant satellites and streams, hints that our galaxy's invisible mass may be broader and denser than Andromeda's. If that's true, the Milky Way could actually outweigh its neighbor, despite its more modest visible appearance. This matters for more than just cosmic bragging rights. When the two galaxies eventually collide and merge, their relative masses will shape the dynamics of the encounter. If the Milky Way is heavier, the merger will proceed differently than if Andromeda dominates. The Milky Way may look gentle and understated compared to its neighbor, but beneath its quiet spiral arms, it may carry more weight, more gravitational influence than we once imagined. Chapter 19. Visitors and Streams. The Magellanic Clouds may be on their first orbit. The Large and Small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way like moons around a planet. But new evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity through space and their trajectory hint that this could be their first close pass by the Milky Way. They're not long-standing companions that have orbited dozens of times. They're distant wanderers just now falling under our galaxy's gravitational pull. encountering it for the first time. If true, their arrival has stirred the outer disk, creating waves and warps that propagate through the structure. The Milky Way is responding to a new gravitational guest, adjusting its shape, its motion, adapting to the presence of these massive satellites. The night sky, quiet as it seems, is full of first encounters, full of meetings between structures that have never interacted before, begetting relationships that will shape the galaxy's future. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas stretching over 600,000 light-years across the southern sky. This is the Magellanic Stream, one of the largest structures associated with the Milky Way. It was pulled away by tidal forces as the clouds pass close to each other into the Milky Way. Invisible to the naked eye, it reveals itself in radio wavelengths, a long trailing whisper of gas marking the path the clouds have traveled. This stream may one day feed new star formation in the Milky Way as the gas gradually falls inward and joins the disk, or it may settle into the halo, becoming part of the diffuse outer regions, a thread of memory stretching between galaxies. It's a connection, a bridge between the Milky Way and its satellites, written in gas instead of stars, invisible but real. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas, and even some stars, move on highly inclined orbits, passing above and below the galaxy's main structure at steep angles. These are called polar orbits, and they're signatures of disruption. These misaligned structures likely come from past mergers, from dwarf galaxies or gas clouds captured at odd angles and retaining their original motion even as they fell under the Milky Way's influence. Over time, some may be pulled into more conventional orbits. Others may continue their tilted paths indefinitely. These polar orbits are records of chaos preserved in motion, visible reminders that the galaxy is not a closed, orderly system, but an evolving structure shaped by the unpredictable flow of cosmic history. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light-years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined stellar winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. The expanding shells swept up surrounding material, compressing it into thin walls of denser gas that glow faintly in certain wavelengths. Over time, the expansion slows as the shells encounter more resistance, but they remain visible for millions of years. Ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are fossils of cosmic fireworks, echoes of ancient violence still visible in the cold interstellar medium, reminding us that even quiet regions of the galaxy have histories of energy and transformation. Chapter 20, Collisions and Breakups. Stars occasionally collide in dense regions. Space is vast and stars are small, so collisions are incredibly rare. In most of the galaxy, stars will never come anywhere near each other. But in the densest regions, such as the cores of globular clusters, where hundreds of thousands of stars are packed into a sphere just a few light years across, stars can pass close enough to interact and even collide. When they do, the result can be dramatic. A burst of light and energy, the merging of two suns into one larger star, or the formation of a rare type called a blue straggler, a star that appears younger and bluer than its neighbors, having been rejuvenated by the collision. These collisions are rare even in dense clusters, perhaps one every few million years in a typical globular, but over billions of years, in the tightest stellar neighborhoods, the structure can rearrange itself through these interactions. In these crowded stellar cities, time moves differently. Space is never quite empty. And occasionally, the impossible happens. Two stars meet. Binary stars can be torn apart by tidal forces. Many stars live in pairs, orbiting each other in gravitational embrace, bound together for billions of years. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole, or through a dense star cluster, or near another massive object, tidal forces can disrupt their orbit. The gravitational pull is stronger on the near star than on the far one. This differential force can stretch and eventually break the bond between them. One star might be captured or slowed, pulled into a new orbit. The other might be flung away at high speed, ejected from the system entirely. In some cases, a companion is hurled out of the galaxy, becoming a hypervelocity star speeding through intergalactic space. These stellar breakups happen silently, in places we rarely observe, a quiet tearing of ancient partnerships by gravity's indifferent hand. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, held by the combined mass of billions of other stars in the vast dark matter halo. But occasionally, a star reaches escape velocity over 500 kilometers per second relative to the galactic center and is flung outward, never to return. These hypervelocity stars are rare but real. They've been detected moving through the halo at incredible speeds, their trajectories carrying them away from the galaxy. Some are thought to be ejected by interactions with Sagittarius A asterisk, the central black hole. Others may be flung out by three-body encounters in dense clusters, or by supernova explosions in binary systems. Once free, they travel alone into intergalactic space, tiny lighthouses drifting far beyond the spiral's edge. They carry the Milky Way's memory outward, becoming solitary pilgrims in the great dark between galaxies. They will wander for billions of years, perhaps forever, alone in the void. The Milky Way contains stars from other galaxies. Not all stars within the Milky Way's boundaries were born here. Some originated in other galaxies, in smaller systems that were later captured and destroyed during mergers. These intergalactic immigrants now move on unusual orbits, often in the halo, far from the disk. They can be identified by their composition, their motion, their chemistry. Stars that don't quite fit the local patterns. Stars whose elements suggest formation in different environments, in gas clouds with different histories. Like cosmic refugees, they bring stories from other places, other skies, other environments. They're scattered throughout the halo, mixed with native stars, indistinguishable except through careful analysis. The Milky Way is not a sealed system built solely from its own material. It's a living mosaic, slowly stitched together by time, gravity, and motion, incorporating pieces from dozens of smaller galaxies across billions of years. Chapter 21, Breath and Circulation, a fountain of gas cycles between the disk and halo. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernova explosions and powerful stellar winds heat and eject material upward into the halo, where it cools over millions of years, condenses, and gently rains back down onto the disk. This cycle stirs the interstellar medium, redistributes heavy elements forged in stars throughout the galaxy, and helps regulate the rate of star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo above and below. The galaxy, in this way, doesn't just spin like a wheel. It circulates. It exhales hot gas upward and inhales cooled material back down, keeping its structure in motion, maintaining a kind of equilibrium across immense spans of time. It breathes, slowly, steadily, endlessly. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life as we know it. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, amino acids, and more. Though not alive themselves, these molecules are chemically rich, formed in the atmospheres of dying stars or within cold molecular clouds shaped by ultraviolet radiation and cosmic rays. They represent a kind of prebiotic chemistry, the building blocks that might eventually lead to life if they find their way to suitable planets. These tiny grains are carried across light years by galactic winds, by the pressure of starlight, by the motion of gas clouds. They settle into regions where new stars and planets are forming, becoming incorporated into the raw material of solar systems. Some of these dust grains may have fallen onto the early Earth, delivered by comets and asteroids, seeding our planet with organic molecules. The galaxy's dust is not just debris or obstruction. It's a cargo of potential, drifting silently through the dark, carrying the chemical seeds of complexity and perhaps life itself. Interstellar clouds may seed solar systems with ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water, ice, carbon compounds, amino acids, and other building blocks of biology, those ingredients may end up distributed throughout the forming system. Comets, asteroids, and even planets themselves can be enriched with these materials. Some regions of the Milky Way are especially rich in such prebiotic chemistry, places where generations of stars have lived and died, enriching the interstellar medium with ever more complex molecules. We don't yet know how common life is in the galaxy, but the conditions for it, the chemical ingredients, the environments, seem to arise naturally and perhaps frequently. The seeds of life may be scattered far and wide throughout the Milky Way, tucked into cold clouds, waiting for the right conditions to spark into something more, waiting for worlds where they can take root and grow. Chapter 22: Extremes and Oddities. Some stars rotate hundreds of times faster than the Sun. Most stars spin, rotating on their axes as they orbit through the galaxy. But some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and close to instability, with equators that bulge from centrifugal force. The Sun rotates once every 25 to 35 days, depending on latitude, a leisurely pace. But these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits. Some spin so fast they're nearly tearing themselves apart, flinging off material that forms glowing disks around them. Their internal structures are different from slower rotators. Their magnetic fields are more complex. Their evolutionary paths are shaped by their extreme angular momentum. Their lives may be brief, but while they last, they spin like cosmic tops, blazing and brilliant in the dark. The galaxy is tilted relative to the ecliptic. From Earth, the Milky Way arcs across the night sky in a graceful band of light, stretching from horizon to horizon, but it doesn't align with the plane of our solar system, the ecliptic traced by the Sun, Moon, and planets. The galactic plane is tilted about 60 degrees relative to the ecliptic. This is why the Milky Way rises at an angle, why its position shifts with the seasons, why it appears higher in the sky at certain times of year. We are part of the galaxy, embedded within its disk, but our own little solar system is angled slightly askew, a small tilted boat drifting through a larger spinning sea of stars. This tilt is a result of how the solar system formed, preserving the angular momentum of the original cloud that collapsed to form the Sun and planets. It's a reminder that even though we're part of the galaxy, we maintain our own orientation, our own perspective, viewing the larger structure from our own unique angle. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled into the organized spiral we see today. Their existence hints at an earlier phase of star formation, a deeper history etched into the outer halo. They have been cooling for billions of years, slowly radiating away their stored heat, fading from white to yellow to red, eventually destined to become black dwarfs, cold and dark and invisible. They carry with them the quiet residue of a time when the Milky Way was still gathering its shape, still assembling from smaller fragments. The disk may be bright and active, but the halo remembers further back, preserving in its sparse population the earliest chapters of the galaxy's story. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels marking the galaxy's edge. They are faint, sparse, separated by vast distances. Some may not encounter another star for millions of years, but they help define the galaxy's size, its shape, its gravitational influence. The Milky Way is not just what we see in the bright disk. It extends deep into the dark, shaped by these wanderers at its edge, by the faint stars and dark matter that stretch far beyond the visible spiral. The galaxy is larger than it appears. Its reach extends further than the light. The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral, perfect and balanced, the Milky Way is subtly lopsided in multiple ways. One side of the disk is thicker than the other. The spiral arms are uneven in brightness, length, and curvature. The central bar is not perfectly centered or aligned. Even the stellar halo is slightly off-center, shifted from the galactic center by gravitational interactions with satellites and past mergers. These asymmetries likely arise from the gravitational tugs of the Magellanic Clouds, from dark matter clumps, from ancient collisions that haven't fully settled. The galaxy is not a perfect pinwheel drawn with a compass. It's a living structure marked by tugs and twists, by uneven growth, by the accumulated effects of billions of years of interactions. Like a spinning dancer whose skirt has been caught by the wind, it shows graceful imbalance, and in that irregularity lies a kind of beauty. The beauty of something real, something shaped by history, something that carries the marks of its past. Chapter 23, Mapping the Invisible. Astronomers map the galaxy using variable stars. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types, like Cepheid variables and RR Lyrae stars, have well-known relationships between their pulsation period and their intrinsic luminosity. By measuring how long a star takes to brighten and dim, astronomers can determine its true brightness. By comparing that to how bright it appears from Earth, they can calculate its distance. This makes these stars incredibly valuable as cosmic yardsticks, allowing us to map the three-dimensional structure of the galaxy. They serve as distance markers scattered throughout the Milky Way, each one a blinking beacon that tells us not just where it is, but how far away. They've been used to trace the spiral arms, map globular clusters, and determine the size of the galaxy itself. They are lights that measure the dark, helping us understand the true scale and structure of our cosmic home. The Gaia mission is revolutionizing our understanding. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise three-dimensional map of the Milky Way ever made. By measuring the positions, motions, distances, and brightness of over 2 billion stars with unprecedented accuracy, Gaia is revealing the galaxy's structure and dynamics in exquisite detail. It has uncovered stellar streams from shredded dwarf galaxies, traced the warp of the disk, mapped the motions of stars in the halo, discovered new satellite galaxies, and tracked the sun's path through space with precision that would have been unimaginable just a few decades ago. With each new data release, Gaia deepens our understanding, turning a hazy smear of stars into a sharp, living map. It's revealing not just where stars are, but where they came from and where they're going. It's astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. We are learning to see the galaxy not as a static photograph, but as a dynamic structure in motion. Every star on its own trajectory, every orbit telling a story. The galactic plane marks a dense path of stars. If you look up on a dark night, far from city lights, far from the glow of civilization, you may see a hazy river of starlight crossing the sky from horizon to horizon. That's the galactic plane, the thickest slice of the Milky Way's disk, the densest concentration of stars. It's not a line but a depth, a vast flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed. Dust is layered in thick clouds. Star formation is common. Supernova remnants glow. The interstellar medium churns with activity. From our vantage point, embedded within the disk, we're looking along the grain of the galaxy, peering through its richest corridors, seeing the accumulated light of billions of stars too distant to resolve individually. This band isn't just beautiful. It's the crowded, humming heart of where most stars live, where most planetary systems exist, where most of the galaxy's story unfolds, and we're part of it. One small system among billions, drifting through this luminous river. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, visible from Earth's southern hemisphere and from equatorial regions. This is where the galaxy is densest, where the concentration of stars reaches its peak, where the supermassive black hole lurks unseen behind curtains of dust. From Earth, we can't see the very center in visible light. Too much dust obscures our view, blocking and scattering the starlight. But the region glows brilliantly in infrared and radio wavelengths, which can penetrate the dust and reveal the core's structure. Even with the naked eye, the area appears more crowded, more luminous than other parts of the sky. The overlapping light of billions of stars creates a concentrated glow, a brightening toward the heart of the galaxy. We orbit far from this center, about 26,000 light-years away, in a quiet suburb of the galactic disk. But when we look inward, when we turn our gaze toward Sagittarius, we glimpse the crowded city at the galaxy's heart, the place where density and gravity reach their peak. We see the Milky Way edge on from Earth. Because we live within the galaxy, embedded in its disk, we cannot look down on it from above and see its full spiral structure. Instead, we see it from the inside, from the edge, compressed into a single arc stretching across the sky. This edge-on view makes it hard to grasp the galaxy's full shape from our perspective. We see stars in all directions, but the greatest concentration appears along the band of the Milky Way, where we're looking through the longest path of the disk. It took centuries of observation, star counts, and mathematical deduction to realize the true nature of what we were seeing, to understand that we live within a vast spiral galaxy, that the band across the sky is the edge-on view of a disk containing hundreds of billions of stars. From Earth, we gaze through the disk like standing in a forest and looking along the line of trees. We do not see the shape we're a part of, only the vastness that surrounds us, the depth and density of the structure we inhabit. We are inside looking out, trying to understand the whole from a single perspective within. The galaxy holds far more than we can ever possibly see. Even with our most sensitive instruments, our most advanced telescopes, our most sophisticated surveys, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in the spaces between stars. Dark matter outnumbers luminous matter by enormous factors and remains completely invisible. Between every star lies vast emptiness, and within every empty space, potential rogue planets drifting unseen, clouds of dark gas that will never form stars, streams of particles and waves we cannot detect, magnetic fields threading invisibly through space. The Milky Way is not just what we see or measure or detect. It is what we suspect, what we infer from indirect evidence, what we long to understand but may never fully grasp. It holds ancient light from stars that died billions of years ago. It holds future stars yet to be born, still hidden in dark clouds. It holds drifting worlds, wandering objects, and questions still without answers. And within that vastness, somehow, improbably, we find ourselves one planet among perhaps billions, orbiting a quiet star among hundreds of billions, floating through a story too wide for the eye to encompass, too deep for the mind to hold completely. The galaxy is larger than our comprehension, and yet we are part of it, intimately, inextricably, made from its matter, shaped by its forces, arising from its long history of creation and destruction. Closing, drifting to rest. And now, the stars begin to dim behind your thoughts. We've drifted together through 100 quiet truths, maybe more, from the warp of the galaxy's disk to the farthest halo stars, from newborn suns blazing in stellar nurseries to long-dead remnants cooling in the dark, from dust and gas to light and shadow, from visible spirals to invisible dark matter, from the supermassive black hole at the center to rogue planets wandering alone in the void. You've wandered through collisions that happened billions of years ago. You've traced the paths of hypervelocity, stars flung into intergalactic space. You've felt the rhythm of galactic years, each one lasting hundreds of millions of our years. You've glimpsed the fountain of gas rising and falling, the magnetic fields threading invisibly through space, the density waves that create spiral arms without being solid structures themselves. You've heard of stars older than the galaxy's disk, born in a different, wilder universe, of chemical fingerprints that tell stories of ancient origins, of stellar streams wrapping around the Milky Way like ribbons of memory, of the slow, patient turning of globular clusters, unchanged for billions of years. You are a part of this galaxy, not just a passenger on Earth, not just an observer from a distance, but a participant in its long and luminous unfolding, a thread in the vast tapestry of the Milky Way's story. The iron in your blood was forged in the core of a massive star that exploded long before the sun existed. The calcium in your bones was created in a supernova and scattered into space, later gathering into the cloud that formed our solar system. The oxygen you breathe was made inside dying giants and released into the interstellar medium when they shed their outer layers. Even the carbon in your cells, the nitrogen in your DNA, the phosphorus that stores energy in every living thing, all of it was created in stars. You are made of stardust, quite literally. The atoms of your body trace their lineage to the earliest times, born from the same matter that now fuels suns, drifts in clouds, and whispers through the cold spaces between stars. Tonight, as you rest, as your breathing slows and deepens, as your thoughts begin to drift like clouds dispersing into clear sky, the galaxy turns on. It continues its ancient rotation, spinning slowly through space at speeds beyond comprehension. Stars are forming at this very moment. Somewhere in the disk, a molecular cloud is collapsing, fragmenting, igniting with new light. Protostars are gathering mass, heating up, approaching the threshold where fusion will begin. Stars are dying, too. Somewhere, a red giant is shedding its outer layers, creating a planetary nebula that will glow for thousands of years. Somewhere, a massive star is on the verge of supernova, its core about to collapse and explode, scattering heavy elements into space. Light is traveling. Photons that left distant stars thousands of years ago are still journeying through space, some of them arriving at Earth tonight, entering telescopes, entering eyes, bringing messages from the past. Silent orbits continue. Stars move along their paths. Planets circle their suns. Moons orbit planets. Everything in motion, everything connected by gravity's invisible threads, everything part of the great dance, and you are floating within it all. A small warmth in the dark, a brief consciousness arising from stellar matter, aware for a moment of the vastness that surrounds you, resting in a spiral arm of a quiet, radiant galaxy, one of billions of galaxies in the observable universe, each one home to billions of stars, each star potentially circled by worlds. The scale is almost unbearable to contemplate, and yet here you are, comfortable, warm, safe, drifting gently towards sleep, part of the cosmos but also separate from it, able to observe it, to wonder about it, to feel small within it and yet somehow significant. Because consciousness is rare, perhaps. Because the ability to look up and understand, even partially, what you're seeing that may be precious in a universe of mostly empty space and lifeless matter. You exist. You are aware. You are made of atoms forged in the hearts of ancient stars. And tonight, you rest beneath the light of those stars' distant descendants. All of you connected across time and space by the simple fact of your shared origin. If you happen to still be awake, you can let go now. There's nothing left to hold on to. No questions that need answering tonight, no mysteries that require solving. The galaxy will continue without your attention. The stars will keep burning. The cosmic dance will go on. Let your eyes remain closed. Let your breathing flow naturally, effortlessly. Let your muscles release their tension completely. Let your mind drift where it will, untethered, free to wander or to settle into stillness. The Milky Way cradles you in its spiral arms. The earth holds you gently in its gravity. Your bed supports your weight. The darkness surrounds you softly, peacefully, without threat or demand. You are home. You are safe. You are exactly where you need to be. If sleep comes now, let it come. If thoughts still drift through your mind, let them drift. There's no rush, no pressure, no wrong way to end this journey. The galaxy turns slowly overhead, a river of stars flowing through the night. And somewhere within that river, on a small blue planet orbiting a quiet yellow star, you rest. You are part of the Milky Way's long story. A brief chapter, perhaps, but a chapter nonetheless. A moment of awareness in the galaxy's 1 3-billion-year history, and that is enough. That is more than enough. Sleep well, dream softly, and may you wake refreshed, carrying with you some small sense of the vast and beautiful cosmos you call home. Good night.